Welcome to another coding session where I'm creating a new programming language from scratch. The language is on GitHub. It's called Plum, and it looks like this. So this, for example, defines a list, a linked list where each node is either empty or it contains some item and the rest of the list. You can define functions like this that percent switches on values. But actually I don't want to focus on the language itself in this session and add any new features or something like that. But instead I want to redesign the compiler. So let me show you how the compiler pipeline currently looks like. This is the Plum compiler. And it's organized into these stages. Each stage compiles to the next stage, and they add, they convert the string of the source code into a tree, and then into a graph, and then they add types and compile that to C code in the end, which you can then compile to an actual executable program. And for example, the test thing, the test program is something that we compiled previously. And it just exits with the status code 42. Right. So maybe I should talk a bit about why I want to change the compiler pipeline. So let me maybe share my iPad screen. Alright, so this is the compiler pipeline visualized. And I'm not interested in the details so much as I'm interested in the general principle of how it works. So down here we have some sort of, our CPU, which can only implement, execute machine code. It can execute that, and that means that we want everything that should at some point be executed to be converted into machine code. Traditional languages like C and Rust, they work exactly that way. They just take their source code and compile that to machine code using something like GCC, or for Rust it's the Rust compiler. And currently Plum works the same way. So Plum, kind of, with an extra step, it's converted to C, and then C is converted to machine code. There's a different family of languages which don't get compiled to machine code directly. Instead, there's an extra program that you have to install, called a virtual machine or interpreter, and this program then executes the actual code. So you have, for example, in Java, the Java virtual machine, or JVM, which is just a program, and this is converted into machine code using, I don't even know, probably Clang or something. I suppose it's written in C++. Yes, so it's written in some kind of, one of these languages is converted into machine code, and then the JVM can execute Java code. Or rather, I guess, Java bytecode. And your Java programs can be compiled to Java bytecode. Okay, so the benefit of this is that rather than needing to compile Java to machine code directly, we can compile to this intermediate bytecode, which is quite high level. It still has concepts like classes and methods in Java, but it's still low level enough that you can like ship this to other devices, and they don't need to have a full Java compiler. They only need this small Java virtual machine. So this is better suited for executing code than the original source code, because it's not just a big string containing code, but it's like, pretty low-level encoding of what the program should do. But it's higher level than machine code. So it's also portable between different CPU architectures, for example. Yeah. Of course, there are benefits to both of these approaches. The benefit of the Java approach is, you can compile this once to bytecode and then distribute that bytecode, and no matter like what new CPU comes out or something, you don't need to change your compiler. You can just implement this virtual machine for the new CPU, or other people can also implement that machine. And now your programs run on this architecture as well. Whereas these programs like C and Rust, they usually achieve higher performance. That's not always the case, of course. You can do some very advanced analysis in Java code and optimize that as well. But basically each interpretation step where you have this dotted arrow that goes upwards, this is pretty expensive. So this right here is expensive, and this is expensive. So the fewer arrows of interpretation we have, the more efficient our code will be, in roughly, generally speaking. Okay, so a lot of these dynamic languages, or a lot of these bytecode languages like Java and Python and so on, they have found a way to run the code even more efficiently. And that is to basically have this JVM. But when you say, hey, JVM, please execute this bytecode, the JVM actually compiles that to machine code on the fly, possibly with extra information about which values actually flow through your program and stuff like that. So basically, you get the power of having something that can be distributed easily and has a low startup time and so on. It's something that is quite low level already, while gaining the benefit of the performance of executing machine code directly. Right. So the big benefit of this approach is that you could also generate new bytecode on the fly. And this is something that some dynamic languages take to an extreme. So let's look at another example, which is Lisp. In Lisp, your entire program is just a data structure, just a huge list, basically. And you have this Lisp interpreter that interprets the data structure. Well, okay, there is, similar to Java, a small step in between, I guess, Lisp data structure. But this step up here is not really a full-blown compiler or something. It's really just parsing your file contents from string into this data structure. And then that is interpreted. And again, the Lisp interpreter is written in something lower level, like C or something. And yeah. So a cool thing that this allows you to do is that your program can just create a new data structure. So in your Lisp program, you can create a new list, which exists somewhere here, right next to your existing thing. This is the same, the same kind of data structure. So yeah, the program can actually create this, and then that can run directly, or be directly interpreted by the Lisp interpreter. So you have this nice circular property of being able to generate new code on the fly, and then that gets executed, and you can use that to generate even more code, and that gets executed. And you don't really have a distinction between programs and data. And you don't have an explicit compilation step. Instead, programs are just data. And you can pass programs around, just pass lists around, and you can evaluate them as you need. Another extreme example on the other end is assembly, which kind of works the same way actually. So usually you have your assembly file containing some instructions, and then you take an assembler which generates that, which converts that to machine code. But of course that machine code can then generate new, machine code is just bytes in memory. So the machine code can create new machine code. Yeah. And I really like this property of being able to build systems that can dynamically, like during runtime, extend themselves and extend their functionality. For example, imagine a programming IDE, an editor, where you can write some code, and then the code is run. But the code can also be used to extend your editor. Like it can run in the same environment, I guess, in the same thing as your original code. It doesn't need to have an extra level of interpretation. It can just be compiled to machine code in a safe way, and then that gets executed directly. Yeah, I want to do that in the long term, just because I like I think this is quite intriguing. And I find it sad that this is constrained to Lisp and assembly and these like mutable languages. I think this is also possible in functional languages with immutable data structures, like Plum. Okay. Yeah, let me maybe switch to my PC, and then we'll look at some examples of how that might work. So, I've recently been reading this book called Self-Sustaining Systems, which it's basically just a collection of papers about languages like Lisp and Self and Smalltalk, which allow you to compile or create new code on the fly and execute that. Yeah. So interestingly, they don't talk about assembly, which is like the simplest version of that, I guess. Yeah, but let's actually just create a simple example of self-modifying code, just so we're on the same page and I kind of get my intuition or concept around what I want to be able to do, and then design how that might look in Plum in like a fully functional language with immutable data structures. So yeah, this is just an assembly file, and yeah, this is going to tell my assembler. I'm using Phasm, which is just an assembler, to only compile instructions. Don't add any header information or anything. So what we will get when we compile this is not something that's executable, but just something that lets us look at what the generated bytes will be. So I think you can do this, yeah. Oh, maybe stump, I think group 1 or something, or minus x, Nope. I guess canonical is fine. Yeah, okay. So this is a file with 2 bytes. And these bytes, they actually represent the syscall instruction. So when the CPU sees these bytes, it's actually going to do something. So they're actually like hardware wires, which after loading the instruction into some CPU internal memory, depending on what the instruction is, some other parts of the CPU get activated, because some of these bits, some of these underlying bits are set to 1, others to 0, and then, using circuit magic, it somehow works. So we can write a program that just exits for now. The rex register means it should contain what the operating system should do, and the syscall instruction tells the operating system, hey, please do something. So when the syscall instruction gets executed, the operating system then looks in the rex register, sees, okay, this program is supposed to exit, that's what the 60 means, and the RDI register should contain the exit code. So in our case, let's say 20, because why not? Yeah. When we compile that, we see that like this is the entire program, just a bunch of bytes. And we can make this into an executable using something like this, I think. Yeah. All right. Hang on. Yeah, now we have a file which we can execute, and it exits with 20. Okay. So the thing is that because these are just bytes, we don't have to put instructions in there. We can just as easily say, hey, please, at this point in the executable, just insert some data. And that's what the DB does. So here we can insert an F in hexadecimal and a 5 in hexadecimal. And this is similar to having a syscall there. Like it's the exact same thing. Let's maybe compile that and see if it still works. Yeah, still works. Okay, so now we can also name these locations in the file. So we can say this is foo. And here we can say, for example, move something into foo, like where foo is pointing at. Foo is just a big number that tells us where in our memory this memory will be. And where that number points to, that's what the brackets mean. Please put an F in there, for example. So even if we put some garbage in here, this will override that with an F, and then this will be a syscall instruction. All right, we may need to move byte, I think. Say that explicitly. Yeah. Okay, so this still works. And let's maybe actually like step through that instruction by instruction. How does it work? I think like this. Yeah, okay. So here we see our code. We have moving 60 into rex for the this right here, this instruction. Then we have this instruction, move a byte into address 4 8D, which is this address right here. Then we have move something into RDI. And then this down here is just some garbage I came up with right now. So that is actually like an add instruction apparently. But as we step through this, we can do that using step I in GDB to step a single instruction through the binary. We can see that, okay, first we set this RAX register to 60. Then we move the byte 0f into somewhere in our binary. And now when I execute this, boom, the source code changes. So yeah, then we move 20 into this other register, oops, and execute this syscall instruction. So the cool thing is that here the source code could change itself. That seems kind of insane, but you can do that, and CPUs are built that way on purpose. Because, for example, you want to be able to download new code from the internet, or like from somewhere, install new software, and then run that without restarting the whole system. We need code to just be data. Yeah, of course, doing this in assembly is like very low level, and you can't do this by hand for bigger things. Yeah, so how could this look in Plum? Basically, I think we need some sort of compile function, maybe, that is built into the compiler. To have some sort of compile function that takes something and gives you back a function. Well, we don't have functions yet, but let's just say a function from, I guess, output. Input to output, something like this. And then it also takes an input type and an output type. And the implementation. Yeah. So that's the idea. Have a compile function that takes 3 arguments. An implementation, which is some sort of low-level bytecode, similar to how the JVM does it, similar to how most interpreters work. And then pass in 2 types, which have to be compile time known. And again, this is like a very cool application, I think, of using types as first-class concepts. And this can then return a function that, like an actual function that maps the input to the output, which you can then call in your code. This is somewhere in between normal compiled languages like C and Rust and like these totally like JIT compiled languages like Python and Java and Lisp, because this is not just in time compiled. You know, this is not I create some data structure and now I'm going to call that so it gets compiled on the fly. No, you need to explicitly call this compile function just to get a normal function out of this. So there is an explicit compilation step. It's not just in time. But you can compile things during runtime. And I think that's like very valuable, being able to create new code on the fly that has the same performance as the original code. Yeah. I'm not entirely sure what I'm going to use this for. I think maybe it would be cool to implement an editor or something that can compile new code on the fly, that can download code, that can basically have a little environment in our language where you can type something and that gets converted into machine code using this compile function, and you get back this function which you can then call and evaluate. Yeah. But again, this is like future work. I just want something like this. So, yeah, I guess the next question is why, like, how could we even do that? Like, currently we compile to C code, and, well, we would need to the implementation is not compile time known, I think. So the question is, how do we even, we need to have some sort of compile function written in C, which compiles bytecode to machine code on the fly. And that's like a huge thing and like a complicated thing to do. We could just say, well, we compile that to C code, to some other C code, and then invoke the C compiler while our program is running, and then work with that. But I think that's quite cursed. And also, like, executing that in the same address space again requires lots of plumbing and is kind of difficult, because we want this resulting function to be able to operate on the same values as our original code. We could just have, I don't know, some data structure, a list or something, and then we compile a function that accepts a list of ints, and then we can just give our original list to that function. So it's like this huge, I guess, universe or, environment, world of values. And you can create new functions that work on these existing values. It's not like their own separate process and you have to copy data over to that. Like, like WebAssembly modules, for example. It's not it's not like that. It's the same the same data world. Yeah. And turns out like our current architecture of compiling to C doesn't work well with that. So what I'm proposing to do instead is to write an interpreter to compile Plum into some sort of bytecode. Then write an interpreter for that bytecode in Martinez, like just like our compiler is just next to our compiler, we also have an interpreter that takes this bytecode and interprets that. And then we can, I think over time, replace that interpreter with something more advanced, something that compiles this bytecode to machine code. Cool. Okay. So I guess let's just get started, like designing something. This bytecode here. The question is, what kind of bytecode do we want to, like, what does this bytecode need to fulfill? What kind of properties? What kind of what are our requirements for this bytecode? I think this should be quite low level, so that compiling this high level Plum code with named functions and types and so on, compiling that and type checking that is quite a bit of work, and also optimizing that. So I want all of that work to happen once during compile time, and the resulting bytecode is as low level as possible. Like converting this bytecode to machine code should be quite straightforward, and we shouldn't need to do a lot of optimizations after the fact. At the same time, the bytecode should be high level enough so that our language guarantees are upheld. So this is a functional language, and data types are immutable. It would be kind of weird if if the bytecode like operates directly on memory or something, and then we can use the compile function to create a function that can modify its inputs, for example. Like that's bad. So the bytecode should be, we need some sort of safety, like it should be quite high level regarding data, regarding what kind of values do I expect in here. It shouldn't like leak memory or segfault. Like it should not be possible to segfault no matter what bytecode you put in here. So yeah, I guess all of the like reference counting and so on, that needs to happen below this compile stage. Like this needs to happen after we converted something to bytecode. So I think just looking at our current wrong VS Code. Just looking at our current compiler stages, I think the bytecode will be pretty similar to our yogurt stage, which means there will be probably functions, I guess, and some notion of types. Yeah, probably not a distinction between runtime and comptime types, because comptime types, they can be basically like compiled out. We can just generate bytecode that operates using these constants. We don't need to have a concept of that in here. Yeah, but basically have these, like switch and calls and so on. Righto. Right. So. Yeah, I should draw something more. So this is our existing compilation pipeline. And what I'm proposing is replacing the C step with something that looks like this. Yeah, with some sort of bytecode. And then write an interpreter that can interpret that bytecode. Interpreter. No. Yeah. And that interpreter is converted to machine code. All right. Cool. Actually, I think the compile function, currently it accepts some bytecode. It can even accept something a bit more higher level, like some sort of, I don't know how to call it, but something that also compiles to bytecode. That's fine too. Because then there's, while interpreting this, the program might generate these new data structures, which then get compiled to bytecode again, and so on. So we have the same like circular loop in here, just like we have in assembly where we can generate new bytes, or like in Lisp where we can generate new lists, which represent programs on the fly. All right. So without worrying too much about the API of the compile function, let's just look at this bytecode here. Okay, I just noticed there are some uncommitted changes. So let's maybe commit them first. Yeah, so we added some error handling. Yeah, I'm just gonna commit everything and that should be fine. Add more error handling. And yeah, next, converting or creating bytecode. Yeah, let's just create a new file called bytecode. And maybe also an extra file called interpreter.mar. And then in the Plum, we import both of those. Import bytecode and import interpreter. And types is something quite fundamental. I'm going to put them up there. Couldn't read file byte underscore code. Interesting. Oh yeah, because it's empty and empty files. Weird stuff. Yeah, I guess let's yeah, okay, so the simplest form of bytecode I know is like a stack-based virtual machine bytecode. So basically you have your interpreter. Yeah, let's merge them for now. We can always separate them later. And your interpreter just has some bytecode, which is actually like a slice, I guess, of bytecode. And each bytecode, or like instruction is nice, I think. Yeah, basically each instruction can either be like, for example, create a new number. Let's maybe look at the yogurt. Yeah, these things should definitely work. And I think the comptime I'm not sure about the comptime things, to be honest. They are these kind of... Yeah, I think comptime gets replaced with these. Or do they? Okay, let's maybe have a list of objects. Yeah. So we have a list of objects, we have a list of instructions, and instructions, like comptime instructions, they just say, hey, please use this object. And when something is compiled into a program, that actually contains a list of objects and instructions that can then, that can maybe index into the list, like object ID, perhaps, where object ID is just basically an int. Index in the objects list. Beautiful. Yeah, so these don't really make sense. You can create a new object, you can switch on something, and again, here we will... Ooh. We need to figure out what to do here. Yeah, creating a new tag. Calling something, sure. Yeah, I think I want to build a stack-based interpreter. So this is going to have a stack. Okay, that's like the first thing. We have a list of objects, and we have a stack, which is a list of object IDs. So basically, you should be able to, for example, for adding two numbers, you would put a 2 on the stack and then a 3 on the stack, and then each instruction just modifies the stack. So this comptime instruction, for example, it pushes an object onto the stack. So for example, you could have instruction.comptime and then some ID of an object that is a 2, and that would basically push a 2 on the stack. Then you have another comptime instruction that maybe pushes a 3 on the stack, and then there's like an add instruction which pops the top 2 elements from the stack and instead pushes another element. Yeah, so the reason to do it like this is that while it takes some code to convert this graph-based or graph-based program into a stack-based one, implementing a stack-based interpreter is pretty simple. Okay. Yeah. So we have a list of objects. We have a stack, which is just an object, which is just a list. And we have instructions, as well as an instruction pointer, which is just an index into the instructions. Okay, and let's say for now instructions can only create a new comptime object, like push that onto the stack. They for now can't switch, they can't do anything. Yogurt instruction also exists. Oh yeah, these are like the fundamental operations which are implemented in the like built into the compiler. Of course, these are also called instructions. Yeah. So I guess let's call these bytecode instruction. Yeah, we don't have these. Instead, we have these built-ins, or like these. Yeah. Okay, for now, let's just say we only support adding numbers. Cool. So the question is, what is an object? An object has, well, it's an enum, I think. It's either, yeah, for now it's always an int. Sure. So let's maybe, comment out the existing compiler and just create a simple bytecode by hand. So we would need an interpreter. You know what, let's call it VM, because it's shorter and just as precise. So we create a VM with objects, instructions, and an instruction pointer. Objects could just be a list of, some objects. Yeah, let's just say 2. We have one object, the 2, and then we have a stack, which is initially empty. We have a slice of instructions, so this will be things like push comptime, yeah, I should add a constructor for that. Object ID takes an int, returns an object ID by just returning an object ID containing the int. Object ID of int, okay. And now this should be able to, oh, hang on, 0. This references object number 0, which is the 2. We can push the 2 times, and then we can add that. Add ints. Initially we start at instruction 0. And now we are kind of not done, but now we are done. Instructions, plural. Okay. And yeah, you should be able to run a VM, which is mutable. Takes a mutable VM, and it's basically a big loop. It gets the current instruction from here. So the instruction pointer tells us which instruction to get. We get that, and then we switch on that. And depending on which instruction it is, we do different things. So, for example, if it's a push comptime instruction with an object ID, we get the corresponding object. Let's maybe add a method for that. We get some ID, which is an object ID, turns, oh, never mind. We can just say vm.stack.push object ID. And when we have this add instruction, add ins, sure. Yeah, it doesn't have any like arguments in there, but instead it just pops two objects from the stack. Yeah, by the way, the top element on the stack will be the last. Yeah, if you say 2 plus 3, basically this will be the 3 and this will be the 2. So it's going to calculate a plus b, but of course it also needs to make sure that these are integers. Or rather, we trust the bytecode that these are integers. So that's maybe, hang on, int, object int. Yeah, this is definitely an int. Same here. And then a plus b is the result, and we create a new object for that. So vm.objects.push something. We push a new object int of that result. And the idea of that is objects.len before we push that, and then we push the result ID. Okay, yeah, I guess. This is the signature unwrap bytecode. Oh yeah, no. We already do get, not get maybe. So this call doesn't work. Okay, unwrap on an int. Okay. A pop. It's an enum. Oh no. Yeah, this is just an object ID. So we need to get the corresponding object. Objects.get that, I guess. Yeah, okay, let's implement get. Takes a VM, returns an object. Oh, and takes an object ID. Returns an object. Just gets the corresponding object from the objects list. So vm.get this, we know that is an int. Beautiful. And maybe also create a new function for creating a new object. And this returns an object ID. Yeah, the ID is just vm.objects.len, and then we do vm.objects.push the object, and we return the original length. So here we can say vm.new object.int. Yeah, and that gives us the ID, which we can then push on the stack. Great. Actually, like pushing and popping from the stack is also very common. So let's add methods for that as well. Pushing an ID to the stack. It doesn't return anything. It just does stack.push. And similarly, popping something returns an object ID vm.stack.pop. Okay, so this is really just vm.pop. Okay. So the last expression doesn't match the return type. True, because this is an object ID with that integer. Beautiful. Yeah. Let's maybe just run that and see what happens. And oh no, this. Okay. So compiling, running the Plum compiler, which is in compiler Plum. Loops forever. Nice. I know why, but let's maybe before add some debug prints. So printing the VM. Where do we do that? Yeah, maybe here. So we should be able to write a VM, and that will just I guess it will write the instruction pointer. Will it though? Yeah, maybe not. It will print the stack first. So stack is this. And then for each item on the stack, for each object, it's going to print the object. So for ID and stack, and VM stack do writer dot space and then the corresponding object, so vm.get ID, which means that we need to be able to write objects, which I think is a reasonable requirement. So writing an object just switches on the object, and currently it can only be an int, in which case we just write the int. Okay, so we write the stack, and afterwards I think we can write the instructions. So for each instruction in the VM instructions, we do something. Oh yeah, let's actually, oh, that's cool. Enumerate them. And then, yeah, we print the instruction. But before, we check if this is the current instruction. So, if the index is the VM instruction pointer, then it's the current one. So if this is current, then we just print, you know, like a small arrow indicator in front of that. And last but not least, we need to be able to write instructions. So that will just be switching on the instruction. and if it's like a comptime instruction with an ID, we write the corresponding ID from the VM. Yeah, we need that. Yeah, I guess. So vm.get ID. Yeah. Otherwise, if it's an add instruction, we just print add. And then in here, we actually call this with the instruction and the VM. Okay. Yeah, this is writer. Oh yeah. Oh, yeah, just print it. Yeah, like this. So we always print the VM before executing. And we should see that the stack, oh, never mind. We should see that get VM object ID. Oh, it's mutable. No, it doesn't have to be mutable because objects are immutable anyways. Yeah. Not entirely sure about that. Well, print bytecode instruction. Oh yeah, this is bytecode instruction. True. Push comptime. Push something. Add ints is what it's called. Yeah, that's what I thought. So the VM is always stuck at the first instruction because we don't advance the instruction pointer. So let's do that at the end of the loop. After executing the instruction, we now increase the instruction pointer. And yes, this will crash when we reach the end. Yeah, exactly. But it should be enough to get a nice intuition about the bytecode. Okay, so the stack is initially empty, and we have a bunch of instructions. The first one is supposed to push a 2 to the stack. So then, after executing that, the stack contains a 2. And we're at the next instruction, which again pushes a 2. So the stack contains 2 2s. And then we call add ints, and the stack contains a 4. But then the instruction pointer is out of bounds. Pretty cool, to be honest. I like that. Mm-hmm. Nice. I guess let's... Like this is now a small bytecode VM. Like very, very small. It doesn't support functions yet, which I think is something that we need. Yeah, and in general, like calling things and having a call stack. But apart from that, it's nice. So how do we do that? We want to support functions. I think basically we don't want... Yeah, so we want to be able to compile new code on the fly. So I think the code actually needs to be an object. Yeah, if code can be compiled on the fly, then it should, for example, also be garbage collected. If the resulting function is no longer used, then the underlying machine code binary thing should be freed as well. So an object can also be code, which will just be this, basically, just a slice of bytecode instructions. And instead of this one instruction thing, we instead have a call stack in here. Yeah, so we have a data stack and a call stack. All of the actual data that functions work on is that works on the data stack, but you can call another function. Yeah, let's call this function. Yeah. You can call a function which is just an object, and then after that function was called, you get back to the previous one. Oh yeah, you don't need an instruction pointer then, but instead the call stack contains a call stack entry, I don't know, and basically it tells you which function is executed, like the object ID, and it tells you which where are we, like the index at which instruction we are. Yeah, this is just a list of call stack entries. Beautiful. Oh, crazy. This is crazy. Yeah, maybe let's add a call instruction. And we just call an object, which will be a function. Oh, sorry, no. Oh, we just call what's on the stack, right? Yeah, that's cool, I think. So the m.stack is not what? It's not a field. Oh yeah, we do have the data stack and the call stack. Oh yeah, we don't have. Oh, we don't really have this. Nah. Yeah, I'm just gonna write function and I'm gonna comment out this. Yeah, and we have a new call instruction. The m.stack is not a field on the VM. Oh yeah, it's the data stack. And this, again, pushes something. Oh no, hang on. It just pushes the object. Beautiful. And yeah. So what do? We take the last thing from the call stack, which will be the current call, the current function call, and we get the corresponding function. So the m.get current call dot, what was it, function? Yeah, function. Yeah, this will be an object, but more importantly, this will be a function. We know that. Oh yeah, and this, because this is a function, this will actually contain the bytecode instructions. So these will actually be the instructions. And then the current instruction is something very similar to this. Get current call dot, I guess, index. Cool. Yeah, if we want to call something, then we really just get the function. Which is just vm.pop. And then we push that to the call stack. Oh, I see. So I guess vm.callstack.push a call stack entry with the function, and we start at the beginning of the function. And this down here won't work in the general case. We need to do that on the previous instruction thing. Like if we call something, then we want to increase the instruction pointer of the current the current call. Can we get like last ref or something? Nope. That's kind of sad. Can we get ref? Yeah, I could use get ref of vm.callstack.len -1. And now this is like a mutable thing. So we can say current call dot index is current call at index +1. Okay. I'm really interested in whether this works. All right, we need to fix this code right here. So rather than just having the int 2, we instead also have a function. And the function will then contain the bytecode. And yeah, like in assembly or Lisp, you can see that functions are just data. A function is just a normal object in Plum. At least that's what I'm trying to do here. Okay, and rather than setting the instruction pointer to 0, we say the call stack has a call stack entry, which will start at the function, hang on, its object with the index 1. So object ID 1, and the index in that instructions is 0. Does this work? Oh, dang, it actually works. What? Okay, so initially the data stack is empty. We push a 2, another 2, we add them to a 4. Cool. Cool. So, what are next steps? Yeah, maybe building a more complicated example, like calling a function, for example. So let's maybe create another function, a function that maybe doubles, or like adds, oh yeah, increases a number by 1. So this would then need another object. It would need a 1, which is 0, 1, 2, 3, index 3. It would push a 3 onto the stack. and then it would say, yeah, this right here, add ints. And then it should return. Do we need, I don't think we need an extra instruction for that. That just implicitly happens when you reach the end. Yeah. So here we get yeah. Here we increase the index by 1. Yeah. But we should also check if we are out of bounds. And if so, then we should just remove the call. So if current call.index is larger than instructions.len, then we do vm.callstack.pop. Yeah. Well, it's to nothing, but previous cases to call stack entry. Oh yeah, this returns something, and we'll just ignore that. Yeah, also this get ref. Yeah, I think it will now crash at the get ref after. It won't. Okay. So let's see. We have the. Oh yeah, we never like call this function, for example. So here we add 2 and 2 to get 4, and then I want to call this function right here, which has index 2. So I want to call object number 2, which is this function, to then increase that 4 to a 5. That took long. Yeah, so we need to push the object and then call that. Is it ever... Yeah, something like that. Okay. Yeah. Let's just see what this does. Ooh. Okay, so we have 2 gets converted to 4. Then we push the function, the increment function. Oh, hell yeah. I think then we are in here, perhaps. And we have the data stack, which is just a 4. And then we push a 2. That's interesting. Oh, yeah. This was supposed to be 1. Yeah, and we get 5 as a result. Nice. And then we get index out of bounds at some point because, well, yeah, let's maybe not do that here, but let's do that when we actually try to fetch the instruction. If that doesn't work, then the current function is done executing. So vm.callstack.pop. And just, start over in this loop. Yeah. Okay, okay. -1 is not in 0 to 8. Not sure I get that. What? Oh, yeah, the length is -1, and then... But why are there 8 things? I think I should print the call stack. Yeah. Let's print the call stack as well. So data stack, we have that. And then we have the call stack with the function in the call stack. Oh yeah. For each call, we print the call function, which is just an ID, and then the instruction. So call that index. Beautiful. Okay. So the call stack is, object number 1, which is apparently the first function, index 0, and then we advance through that function. Now we push another function, and we call that. So yeah, this is it's like the one past the end of the function body. And here we have those 2, which, yeah, basically is the new function being called. Makes sense. So that function pushes a 1, a 5, a 5, and then that function returns. Hell yeah, and then that function returns. Okay, amazing. Okay, yeah, so let's just... Oh, yeah, we never break out of the surrounding loop, but we should do that here. So if the call stack, is empty, then we'll just break. Yeah, a small bytecode VM, stack-based, that can execute code. That's pretty cool. That is pretty cool. Okay, yeah. We can push new ints, we can call functions, we can add ints. And functions are just objects. Programs are first-class values in this VM. Okay. So how do we compile our code to that? That would be the next question. This is quite low level, to be honest. But it's simple. That's cool. Yeah, let's maybe first add a constructor for the VM and make the API a bit nicer. So you should be able to create a VM by doing what exactly by I think the objects are all you need. Yeah. So just have objects, which will be a list of objects. Yeah. And that gives you a VM with those objects, with an empty data stack, and let's say for now also an empty call stack, because then you will have an extra function for calling a method or calling a function in here. So this will actually be called call. You give it a function, which is an object ID, and arguments, which are object IDs. And it will just... Oh yeah, no arguments. No. Yeah, it will push. Yeah, maybe let's add arguments, because why not? Yeah, arguments are just, I guess, a slice of object ID, and the arguments, they just get put on the stack. It's as simple as that. So for arg in args, do vm.push arg. Perfect. And then we push the call entry, so vm.callStack push call stack entry with the given function and index 0. Nice. And then we loop. Beautiful. So here, rather than doing this, we can just create a VM from this, list of objects. And then we can say, hey VM, please run this function. It doesn't take any arguments. So yeah. Oh yeah, call this function. True. Okay. Nice. I mean, compared to compiling to C, this VM will be super slow. But I think for simple programs, it's enough. It allows us to implement a compile function, because then we would just have a bytecode instruction compile. And then we can, because we are in Martinez, we can then just basically use our existing compiler pipeline again, or at least parts of it, to compile something to bytecode instructions and just push that into this objects list. And now you have compiled a function, we can always make this more efficient by lowering this to machine code later on. But for now, I just want to get this architecture working at all. Cool. What else? What else? I think let's compile. Let's just attempt to compile our code to this and then add new instructions as we need them. So yeah, the first part of our pipeline will remain exactly the same. Yeah, it's just that rather than compiling this to C, we would instead compile this to, a list of objects, basically. So yogurt to bytecode, I guess. And then we create a VM, which will just be a VM of those objects. And we need to call some object. Yeah, okay. So I guess this is some sort of bytecode, and here we do something. Converting things to bytecode. There were no definitions named to bytecode. That is true. Yeah. I like that the VM is like completely self-contained in here, and there is no 2-byte code in this file. Yeah, let's maybe create a new file, 2-byte code that just compiles yogurt to bytecode. And what exactly is bytecode? Well, I guess it will have some objects, maybe. And like an entry point, which will be the main function. I don't know, something like this. Okay, so yogurt. Bytecode refers to lists, but yeah. Yeah. So how does let's just look at how compiling to C code works currently. Yeah, we have some types. Okay, we mangle things. We don't need mangling or any of this header thing and so on. Yeah, no, let's just get to the actual functions and then add things later on. We don't need function declarations separately from the function bodies. There are advantages to doing this in like having a simpler compilation target than C. Okay, so let's see. Yeah, I think all of these functions, they should be objects, right? So we need to basically build up a list of objects. I'm just realizing all of these yeah, these calls here, they depend on concrete object IDs, which, later on will be like addresses or something. But of course, those will change you know, when you compile something, Oh, does this, I think this needs a VM already. I mean, that's pretty cool. That is super cool. Yes. What? Yeah, while we compile our code, we need to like allocate new objects and so on for those functions and constants that are used, and yeah. Crazy. Honestly, this is kind of crazy. So, how do we do that? Yeah, no, we don't have objects in here. We just add them to the VM. Yeah, for each function in the VM, we basically want to we want to map each function to an object. That's like the first thing. And when we compile the function body to C, which we do down here, yeah, we may reference other functions. Yeah. So here we call these other functions. In our case, we need to call specific objects. So we kind of need their ID already. Yeah. Well, so let's add yeah, let's first map each function yeah, let's map each function to a function object. You know, signature to object, and this is just a map from yogurt signature to object ID. And for each function, we just create some garbage object for now. So vm.new object, okay, I don't know, int 0 for now. And this returns a new object ID, which we then put into this map. So signature to object, put fun dot index dot signature dot key this. Okay, so now we know which objects our functions map to, but we need to override these objects with like actual usable stuff. Yeah, so here we do this. We have the signature and the actual function. Yeah, let's not worry about return types and so on. Yeah, instead we just want to convert the function body into bytecode, right? Like fun dot to instructions, maybe. Basically create this list here. So converting a yogurt fun to a slice of, what was it? Bytecode instructions. Bytecode instructions. We need to do that. Yeah, but then in here we can replace those objects, like vm dot objects dot get ref of the ID of signature to object get ID is yeah, let's call it signature to ID. The object, yeah, we get the object mutably, and we say, hey, this is now a function with these instructions. And that's it. Yeah, kind of like this, I think. Yeah, okay, and the last to bytecode, this should just return an object ID, I think, which will be signature.get, you know, like the main function, main, was it int, I think? Yeah, oh, the idea of the main function. Oh. Oh, right. Even better. You got signature main list int, like this. Hang on, yogurt signature slice of yogurt param, of course. So yogurt param dot runtime with a type, right? So plum type dot, is it int? I think it is. Or is there like a primitive? And converting that list to a slice. Yeah, this is kind of a lot of stuff. Okay, yeah. Okay, so we basically create objects for each of these functions, like placeholder objects in here. And then we compile each of these functions into a function object, and then we return the main function ID. So the only remaining thing is converting a yogurt fun to bytecode instructions, which may also add new objects to the VM. So I think this also needs a mutable VM. Okay. Crazy. Yeah, I should like document, you know what, let's do that. Let's document things first. So bytecode. All Plum code is converted into a simple stack-based, a simple bytecode for stack-based VM. Yeah. A stack-based VM interprets all Plum code. Yeah. like compiled code lives in the VM as function objects. You can compile new code on the fly, and code is garbage collected just like any other objects. Yes. Okay. This file contains the VM, the bytecode definition, and the implementation of the VM. Yeah, to see how yogurt gets converted into bytecode, check out to bytecode.mar. Yeah, okay, I think that's fine for now. Okay. Cool. So converting a function to some bytecode instructions. Let's just look at how the C compiler, like the compiler to C, did that. Boom. Yeah, so we iterate over the function body, which I think makes sense. Yeah, I think that's fine. Although we probably need to do that for other bodies as well, so. Yeah, let's just do it like this for now. So yeah, we don't need this annotation thing. We don't need this, or this, or this, or this. Oh, anyway, some of that was useful. Are you getting the expression from the function? Yes. And then switching on the operation, panic. Okay, I guess uninitialized. Interesting. Interesting. Let's just push, or like do nothing, I guess. Yeah. Like this should never be reached, I think. This was only in the case of a never type. So then we have comptime. What was that about? Oh yeah, if we have comptime value, and note this is not like an object, this is a yogurt value. A yogurt value, exactly. Which contains a kind, and yeah, this is this. Oh, yeah, so we need these values in our code. Huh. Yeah, let's add them to the VM. Let's say we have some new objects. Okay, ints get mapped to ints, and strings get mapped to string. Types. Oh, an interesting one. I mean, you can't really I think in the bytecode you can't really inspect types anymore. So let's say those get mapped to strings for now, and we can change that later on. Tags. Yeah, I guess that. So we have tags. Interesting. With an object ID. Yeah, we added strings and tags. So, by the way, these objects currently just live in this huge list, and we use object IDs as to reference other objects in this list. So here, for example, we use object IDs. Later on, we will use something more efficient, like rather than keeping a list of objects, we will just let them be on the heap somewhere. And instead of object IDs, we will use pointers to objects. So, for example, if we have a tag, this will actually just contain like a set of other object, like a pointer to the payloads, you know. Okay, so for a tag, we print some stuff. We print the tag name, which is tag.a, I think, and then the items there. So for each argument of the tag, I guess. Nah. So for argument and tag in the payloads, we basically print that argument as well. Oh yeah, let's actually say we can't write objects, but we can write, object IDs if we know the objects, like something like this, because objects are not self-contained. Before they were self-contained, now they can reference other objects. So to print them, we actually need a VM. Fun. So yeah, we can just get the object from the ID, from the VM. That gives us an object that we can then use, and in here we can print the arg using, by calling this method recursively. So write the arg using the VM to get the objects. Okay, yeah, and in here we don't do this, but instead we print a space, and then we write the ID using the VM to resolve objects. Okay, so back, compiling yogurt to code. If we have a comptime value, we need to map that value to a new object. Yeah, we don't need indentation for that. We just switch over the, what kind of value is this? If this is an int, yeah, then we just create a new object. Object.int. Easy. If it's a string, we create a new object, string. Nice. If it's a type, we create a new, and we create a new string as well. This is nice. So vm.new, I guess, object.string. Yeah, something like this. tag, well, what's going on here? Wait, we don't set the payloads, do we? No, tag.b is never used. That's not correct, I think. Yeah, so let's map the arguments first. So we need a list of object IDs, and for each argument in these arguments, we convert that to an object. Oh yeah, so let's maybe create a helper function to object. We can give it a yogurt value, and it will create new objects on the VM. And it will actually do what we did here. So if it's an int, it will create a new int object. If it's a string, it will create a new string object, and so on. And if it's a tag, it will then recursively call, arg.toObject using the VM. That will result in an object ID, which we can then push to these arguments. And then it will create a new object.tag in the VM with the name and the mapped arguments. Arg is not in scope. What? But arg is in scope. What is going on here? No, maybe this will get fixed, probably. Just an analyzer bug. So a value will just be mapped to an object. VM. Oh, never mind. Just value dot to object on the VM. Boom. Oh yeah, and the corresponding bytecode instruction. We need to add that as well. So we have a list of bytecode instructions, and here we just push a new instruction. So instructions dot push bytecode instruction dot comptime, or dot push, yeah, something like this. Push comptime, and we have a value. Yeah, push comptime is maybe a bit weird. Push value, let's call it. Or just push object. Yeah. Okay, yeah. Switch is kind of complicated. We're gonna skip that for now. We will add this later, but Okay, for a tag, we need a bytecode instruction to create a new tag, I think. Yeah. Let's add that tag. Yeah, this may get to the arguments to the tag are probably on the stack, I guess. Yeah, So let's say this is a tuple of the tag name, you know, and the number of arguments, tag, you know, symbol, and number of arguments or payloads. Okay, so here we just push a new instruction, similar to what we do up here. We just say push new bytecode instruction dot tag, like, yeah, tag, with the tag symbol. Oh, and now we need a way to reference previous instructions, or like previous expressions. And on the stack, we don't have that yet. So I think we need, oh, yeah. So I think we need some sort of, yeah, some instruction that duplicates something that was previously on the stack and puts that like at the top of the stack again, you know, the same object ID. So if we encounter a tag, we can just you know, pick out the objects that we want to add, push them on the stack, and then emit a tag instruction. Yeah. Okay. So we basically need like a model of the stack, something like that. A stack being a model, like a, let's say, a list of expression indices. So we know which expressions are on the stack. And after each expression, there should be one additional expression on the stack. So in here, we just push that. We push stack. Let's maybe not call it stack. Let's call it like stack model or something, you know. Like, this is basically a model of how the stack will look like. Yeah. Oh, also the function parameters should be, they will be on the stack. So for parameter and the function parameters, oh, I don't know, something like this. Not sure at all. Yeah, and in here we say stack model dot push expression, oh no, just ID. Oh yeah, and these are IDs. That's cool. Yeah. Okay. Yeah. I quite like that. Yeah, params. No? Body. Sure. Cool. Stack model dot push. Oh, it's a yogurt ID, which is actually fine, right? Yeah, let's turn this into a list of yogurt IDs. Cool. And then we can reference previous. We should now be able to reference previous expressions. So we go over the arguments. And we basically want to push that. So instruction, basically this. Push, not push object, because we don't know the object ID, but instead push, and then there is some offset into the stack, like stack, push from stack, maybe. Offset from the top of the stack. 0, top, 1. Yeah. So if we have an instruction push from stack 0, this would just duplicate the top item on the stack. If we have push from stack 1, if the stack is something like this, 2, 3, and now we do push from stack 1, we would push the 2 again. So it's basically a way to push something that was previously on the stack, push that on the stack again. So what's the offset of this ID on the stack? Well, it's basically the distance like the distance from the end of the ID. So let's add a function, helper function for that. Distance, like find distance from top. Yeah, we have a stack model, which is just a list of yogurt IDs. We have an ID we want to find, and we get back the offset from the distance from the stack top. So we are going to iterate over the stack in reverse. I think there was like this. Something like this. Yeah, if the entry is the ID, then we just return the index, but like stack model.len minus entry index -1. Hang on, let me think about this. So let's assume we have a stack with 2 items inside, and the ID is the top ID. Our enumerate will, oh, never mind, we don't need this, because we are already enumerating the, like from the back, There was a ref iter, and I think there is some way to iterate in the reverse order over, oh, does it only work in slices maybe? Yeah, it does. So yeah, here we panic, ID not on stack. Cool. So then here for each argument we can basically look at what is the offset. Like stack model find distance from top of the argument, and we push that to the stack. And then we push this tag instruction which combines all of these pushed arguments into a tag. Great. I like that. So then, calls. For each argument in the call arguments, we do what? Yeah, for calls we do something quite similar actually, I think. Like we first push all of the arguments onto the stack. And then we actually call the function. So like call.receiver, this will be this will be a yogurt signature. So we know which object this will be because we have this map, which we'll also need here. Yeah. And in here we can say signature to ID, get the receiver. This gives us the object ID of the function that should be called. So here we can push the the call instruction. Hang on, we can push the function that we want to call. Yeah. And then that just immediately works. Nice. Next up, instructions. Well, depending on the instruction, we do something different. So if the instruction is add-ins, well, guess what? We will just add a bytecode instruction add-ins. Yeah, and the others, let's just have a to-do for now. Nice. Hang on. This takes an argument, right? I think so. Well, for now, let's just. Okay. Yeah. Oh yeah. In the end, we need to return from functions, and then we need to clean up the stack. We need to like remove all items except the item that is returned. So I think the easiest way would be to just push the item that is being returned. So instructions dot push Yeah. So we push a new item to the stack, and we push the return value to the stack. Yeah. And then we need some way to pop all of the temporary expressions below that, which are on the stack. So how do we do that? I guess let's add a new instruction for that. Pop n below top. Very specific, but pops n objects below the top. Pops n objects, skipping the top object. Amazing. So yeah, we can just add that instruction as well. So pop n below top. How many do we want to pop? Well, the amount of parameters that we have plus the amount of expressions that we have. Yeah. Body is not in scope. Oh yeah, it's fun body. Oh yeah. Yeah, for now let's say it's fun body, and then we can always extend that later, but let's put it to 2 in the switch. This is, oh, I see. Oh yeah, these need to be converted to a slice. Okay. Now, no more errors. Well, okay, some errors. Oh yeah, we can do that. Oh yeah, and here we need to give the signature mapping in there as well. Cool. Yeah. No. No errors. Great. True. So in the Plum, we also need to import stuff, perhaps. Yeah, we do. We don't need this. Nope. Yeah, converting this to bytecode already needs a VM. So, well, VM is VM with an empty list. Yeah, I should add a new VM constructor that doesn't take any arguments. Okay, but in here we can now compile something and pass the VM as a new thing. And this returns an object ID, the object ID of the main function. So we can then call the main function with an int. So let's call it with 1 maybe, or 5. So we can just create a new 5 in the VM and then call the main function with 5. Damn. To be honest, that is pretty cool. Like, super cool. Yeah, let's maybe see if this works. I mean, this definitely doesn't work because switches don't get compiled. Oh yeah, and in the VM bytecode thing, we apparently changed a few things. Yeah, this is now called push object. Oh, right, we need to handle all of the instructions. Push from stack. Well, vm.dataStack.get vm.dataStack.len -1 -offset. Yeah, this will result in an object ID, which we then push on the stack again. Then pop n below top vm.dataStack.pop. Yeah. And then, hang on, vm.pop. Yeah, where is it? And then, like, n times, we also pop more values, and then we push the top value again. Great. Great. Okay, so tag is another one. Yeah. Tag basically has args. Like tag, okay. Yeah. Symbol is tag A, num args is tag B, and here we just get all of the args, I guess, which will be an uninitialized slice. There is definitely a cleaner way to do this, I think. And for each, for I in 0 to num args, we basically pop the argument, and that will also be the last, like that will be, we need to build some sort of list or slice, but from the end. And there is no way to do that cleanly, so we just say args.getRef of num args, something like this. Yeah, we fill this argument buffer up from the back with the elements we pop from the VM. Okay, yeah, then we create a new tag. So vm.new object.tag with the symbol and also the arguments. Hang on, oh, tuple. Yeah. Okay. This call doesn't work. Slice. Oh yeah, it is already a slice. Cool. Yeah, we also need to ignore that newly... Oh, hang on. No, this is a useful error. Because we want to push that newly created object to the stack. I like it when compilers are like, hey, this is probably wrong. Do something about that. Right, so calling something first pops the function, and then yeah, we need to pop the arguments as well. Oh no, we just call that function and the arguments are already on the stack. So when we execute instructions in this function, the function will then consume those arguments. Okay, let's give this a run, and this will fail for the switch with a to do. Never mind, it will fail because we intentionally put an error in there to test the error handling. Oh. Yeah, this returns the string. Yeah. Oh, to do. Yeah, exactly what I imagined. Okay, so yeah, converting a switch to instructions doesn't work yet. Let's maybe do that. Sure. Yeah. Hang on, converting a switch. Yeah. Should be here. And this to do. So basically right now we don't have control flow in our bytecode. We just have things like push an object, basically modify the stack. But the instructions are always executed from top to bottom. Sure, they can call other functions and then those instructions will be executed and that function returns. And well, yeah, but you can't have any control flow that depends on data. Yeah. So I want to change that. I want to, like for switch, we need some way of moving through the, having some sort of jump, perhaps, a go-to in here as an instruction, which jumps inside of one function. So we can like skip sections of the bytecode. Yeah. Okay, I mean, we only have switch for that. Yeah, so let's, I think WebAssembly has a nice thing, a nice design for that. Whereas they have a jump table instruction or something like that. That's not really WebAssembly, but sure. Yeah, basically, you have this one instruction. In our case, that would be like a map for now. You have some condition, which is an object, and it should be a tag. And then you have a table that says, hey, for this tag, jump to this instruction. For this tag, jump to this instruction, and so on. Yeah, so we need some sort of jump table, which is mapped from string to int, like instruction index. And let's maybe also add an unconditional jump that just jumps to something. Oh yeah. Oh. Yeah. So jump just jumps to this instruction index. Yeah, pops an enum. Oh no. Peaks, like it looks at the top value of the stack. At the top value. An enum. Depending on the symbol, jumps to different. Yeah, something like this. Cool. Okay, yeah. So, in here, for a... Yeah, let's first implement them. Why not? So we have these pop instructions, then like push and pop, then several jumps. So we have, yeah, let's maybe add the simple, let's move the simple jump first. Jump to some index, you know. Hang on. Well, sorry about that. So, right, switching. Let's just let's handle that in here. So when we jump to an index, we really just want to change the index in the current call. Yeah, so you know, from the call stack. Yeah, so let's just I guess get that. Here we have the current call, which is a mutable thing. Here by default we move to the next instruction, but if the current instruction is a jump instruction, then we basically override that default of the next index with that index. And if it's a jump table, then we just look at the top element. So kind of like pop, but you know, not really. Like last, I think, or like, yeah, data stack, but last. And that should be an enum. So yeah, this is an object. Sorry, this is an object. Yeah. And then that object should be an enum. So object.enum. And enums save a tuple. And we want to get the symbol. And then based on that symbol, we want to jump somewhere. So the index we jump to is table get symbol. And then we do this. Beautiful and quite simple. Okay. Oh, yeah, right. Tag. So now we want to compile a switch to that. So yeah, we need to push like a jump table, but we don't know the entries yet. So for now, let's just put a placeholder in here, and we will replace that later on. Then we will, we will remember jump table index is instructions.len. So we can later on replace, like override that that item in this instructions list. Yeah. Cool. What do we do in the C code? Let's just uncomment that and then adjust it as needed. So we do a switch on some condition. Yeah. Okay, so we get the type. And now we basically want to convert each switch case. So yeah, we don't save tags as ints right now, but just as strings. Yeah, so for each case, we basically, hang on. Yeah, we do something like this. If it's this case, then we want to do something. And in reality, these will just be next to each other. Like all of the different switch cases will be bytecode instructions right next to each other. So let's just replace them with yeah, let's save a table in here. Like actually a map from string to the int. And for each case, we know the symbol, and the int should be the index of the instructions that should be executed. So right now, let's just take the current instructions. So instructions.len. Yeah. Getting the parameters, like that's something we'll look at later. And then the value will be converted to instructions, which doesn't work right now because, well, our to instructions only works on entire functions, not on bodies. So we need to adjust that. Okay. Yeah, but apart from that, I think that's pretty cool. So let's maybe like separate this out and turn this into something simpler. You know, fun is yogurt fun, and we do need the fun in here to get a referenced expressions, for example. But really, we just want to lower this body. Lower a body. Which needs the fun, which needs the VM to create new objects, which needs the signature to ID to call other functions, and it needs the mutable list of instructions, because rather than returning this, it just accepts a mutable list. Bytecode instruction. Yeah. So this is basically the input to this function. It appends things to this instructions list, and these are all like helper things that it needs to do that. And I'm just realizing I modified the wrong signature. Yeah. Okay. Oh yeah, stack model is something that we also need. Right. Stack model is a list of yogurt IDs. And then this will live up here. And here we just say function.body.toInstructions. Or like, you know, compile to instructions. Yeah, it takes the instructions list, the stack model, it takes the function, the VM, and the map from signatures, from function signatures to IDs. Oh yeah, body doesn't exist. So what? Oh, it's a yogurt body, right? Yeah. Okay, and in the end, we just return the instructions, whereas here, this doesn't need to return anything. We just iterate over the instructions. We get an instruction from the function, lower that thing, and we don't need to return the instructions. Okay, yeah, and the to-dos, the switch cases, they just call compile to instructions with the instructions that we have. The stack model, the function, the VM, the signature to ID. Okay, yeah. Very, very cool. Okay, so what about the function parameters? Or like the enum payloads? I think basically we need a way to get the enum payload out of an enum. Like we need a new kind of instruction, you know, some sort of get enum payload or something. Payloads, plural. I mean, why not, you know? Consumes an enum, pushes all its args on the stack. Nice. Oh, consumes a tag. Nice. Yeah. So we compile the cases, and then in the end we adjust this jump table. So instructions, get ref of jump table index. Yeah, we set that to a bytecode instruction dot jump table of the table. Very cool. And then in here we push, oh yeah, we put something into the map. We emit this new push enum args thing. What was this? Get enum args. Maybe unwrap, or like unwrap tag, maybe. Untag, you know, we have tag, which consumes some arguments and a symbol and pushes tag. And then we have untag, which consumes a tag and pushes its arg on the stack. I like that. So we put an untag instruction in here, which will push all of the payloads of the enum and consume the enum itself. Is that what we want? Hang on. I am not sure. Oh, yeah, switch condition. We need to push the switch condition here first. Yeah, so instructions dot push bytecode instruction dot push from stack. Okay. Yeah. So we push the switch condition onto the stack. We have this jump table, which we later replace, which only looks at the top element of the stack and then jumps to some index. And inside of these branches, we then have this untag instruction, which unwraps the top tag, you know, and yeah, it basically does this right here. Then compiles the tag value. Then it should oh yeah, this already, you know, this calls ourselves recursively, and that means it also pops all of the intermediary expressions as well as the parameters. So the untag thing here, right here, the resulting expressions are also consumed by this. So the only remaining thing on the stack, compared to, you know, here right at the beginning, is that we now have the value that the enum should evaluate to. Yeah, so the only thing left to do is to jump to the end of the switch. So var end is instructions.len. Byte code instruction.jump to 0. This is a placeholder, and jumps is like we need to, we don't know how many instructions will be in the following switch branches. So what we do is we just compile them and then later on fix the jumps. Yeah. Okay, so yeah, we calculate the end. In here we say end jumps dot push instructions .len, and then we calculate the end, and for jumping end jumps we say instructions dot push oh no, not push, but instructions dot get ref of jump. Okay. Okay, yeah. In here we still need to handle the untag. So this is not called, oh, this doesn't even exist yet. Sure. So untag, what does it do? It just pops the top thing, yeah. Tag is vm.pop.tag.b for arg in b. Yeah, tag.b. We push that, so vm.push arg. Okay. Oh, okay. What is going on here? Oh, this is like an error in the compiler, I think. Oh, why? Okay, so maybe of tuple 2 of string and slice of object ID. Maybe of tuple 2 of string slice of object ID. Hang on. Tuple 2 of string slice of object ID. Yeah, this right here. I think this tag is never created, so there's something not compiled. Again, the compiler error, it's weird. Really weird. Okay, object tag. Why does, like, this should create an object tag. Or the tag should create that. Here. Yeah, object.tag with symbol and args. Well, this kind of sucks, to be honest. Like, where is that even? What? It's not in the map. Okay, so you want to get some type definition of that type. Oh, yeah, let me do something like really, really hacky for now, which is just to, so there's this static type, which some parts of the fuzzing pipeline use to basically support function overloading based on types instead of based on types where you don't have instances of. So I'm just gonna create a thing, tuple2 of string and slice of object ID. Ooh, okay. So I think if we fix this, then yeah, then the previous error will disappear. Oh man, that's kind of sad. Oh yeah, because this is, and maybe so we can unwrap that like this. Okay, and in here we say vm.pop. Well, yeah, that just returns an object ID. So then we need to say vm.get to get the underlying object. This is a tag, we know that, like this. Okay, so compile to instructions to do. Oh yeah, I mean, sure. Oh, but those are all, yeah. Okay, yeah, we can, like, I can work with that. Yeah, in fact, let's just uncomment all of this and do something like very similar in each of these. Let's just say instructions.push bytecode instruction dot and then that. Okay, and in the bytecode we also need to handle all of these. So down here we should switch on that and not only do that, but also handle these others. So subtracting integers. Gets the top two integers, then subtracts them. Oh, ID is not even used. Okay, and instead of result, let's just inline that there. Okay, subtracting, then multiplying ints. Yeah, should work just like that. Dividing ins, taking ins modulo. Ending ins, like that. That's, I think you can do that. And nope. Ooh, how do you do that? Is there or? No. How do ints work? Let me just look in the standard library. So you can add them, subtract them. Oh yeah, there was an OR function. Oh yeah, but it's not an operator, it's just a normal function. I guess that makes sense. Yeah. And then XOR. I think that's this. Yeah. Yeah, comparing ints. Ooh. Okay, so this is interesting. This should get both integers. And then, yeah, it should push a new tag. So based on, you know, A compared to B, if it's less, then it should push. The tag should have, you know, a symbol, which is something, and it should have payloads. Payloads are just nothing, so an empty slice. Yeah. Oh, okay. So we push a tag that corresponds to that. Concatenating strings. Well, that gets two strings, and then it pushes a new string that is just, you know, A and B. Okay, crashing the VM takes a message. And then panics with that message. Cool, 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 cool. All of the built-ins. Oh, that takes a long time. Let me see what happens here. Oh yeah, this, like this should, we should be able to remove that. Yeah. Maybe let's print. Compiling to bytecode and then running in the VM. Beautiful. Compiling to bytecode. Okay, and that takes super long for some reason. Interesting. Why? Here we have. Oh no, that's not compiling. Compiling is here. Compile to instructions. Yeah, let's just print the AD, I guess. Two and 9. Interesting. So we are compiling some sort of switch. And a call. Built-in compare ints. Yeah. Okay. Okay, and then we have this expression. Mm-hmm. 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 I'm not sure what to do here. Like, why does this get compiled multiple times? Hang on. The later one is the switch. Which means this happens. So we push something, we push another instruction, we take the type of the enum, which we don't actually use, do we? Nope, we don't. Well, so yeah, we build a table, which means for all of the switch cases, we drop them. We compile them in case.value.toExpression. Instructions don't push what? How? Like, what is that? I'm not sure why we ever compile a previous instruction then. Compiling body 2 and 9. So instruction 2, let's see, what is it? No, that's just a simple call. Why does the call compile that other instruction? It doesn't. It just, yeah, like this doesn't call compile. This does call compile, but only on the case value, which should be fine. Strange. Very, very strange. Amazing. Green tea. It's very cool. So we have a switch where we basically say, oh, I see. So the switch condition is yogurt ID 2. Okay, yeah. But that doesn't mean that we want to compile that 2. That does mean that we want to push that 2, to the stack. But does the condition doesn't get compiled again, does it? No, we just take the condition, find the distance. We don't compile anything extra in here. And by compiling case.key. Oh yeah. Okay, so compiling case less. I guess, okay. So we have this switch, and if it's less, then we have this. Hang on. Yeah, probably like a really huge switch. Yeah, this is from the yogurt expression and its type. This is from the switch. Yeah, this is that. Oh yeah. Oh, I see it now. Like, I don't see the error. I see what the code means. So the less case contains the yogurt IDs 3 and 6. Okay, and returns 6. The equal case contains the yogurt IDs 4 and 7, returns 7. The greater case contains 5 and 8 and returns 8. That is very fine, I think. So why is 2 compiled? That doesn't make any sense. Why is the condition compiled again? What? Cases is less is this. So compiling the case less, which is just this yogurt body with 3 and 6 inside. Hang on, let me add some more logging maybe. I compile the instructions, compiling body, and then body debug. Yeah, compiling body, boom, this yogurt ID. So why does it compile the ID number 2? Oh no. Okay, because this uses the function body. Oh man. Is there any other fun in here? Yeah, that's fine. Yeah, no, this should be the body. Yeah. Okay, so this should compile, right? Oh no, panicked. 1 is not on the stack. Interesting. Oh, right. So we have a body with some IDs inside, I guess. I see. And we need to adjust the stack model as well. Oh yeah, for each instruction that we emit, we also need to adjust the stack model, at least if we also observe the stack model. So in here, when we have some comptime thing, after this huge switch case, we just push the ID. That's fine. That's also fine for the primitive. Hang on, no, it's not fine for the primitive ones. Well. Gotta fix that. Okay, so for the switch, we push bytecode instruction push from stack. We push the condition. We push the condition like a jump table placeholder. Then we want to compile the cases, where we basically push this untag thing. And then for each parameter in the corresponding enum case, which we just removed, that was this nice, yeah, this right here. Now let's do this a bit more cleanly. So we save where we are. We push the untag thing, and in the type.get, you can do that once at the beginning. Yeah. Okay. Yeah, so here we have variance.get case.key. This should return a list of oh, no, never mind. Not even needed. Not even needed. We can just push the body for param in case.value do stack model dot push param. Oh yeah, this is a body params, something like this. Yeah. Wait, stack model, where's stack model? Stack model should be mutable. Okay. Sure. Yeah, then basically for the other instructions, we also need to adjust the stack model. So stack model.push param, yeah, and then we compile that body. Yeah, in that case, the stack model will only contain a single instruction. Yeah. So let's say stack model dot pop. Okay, yeah, I think that should be fine. So here we push the arguments, we push this instruction that cancels each other out. Okay. Call. Very similar. Yeah, instructions. Yeah, no, they are kind of more complicated. Yeah, the add instruction consumes 2 arguments. So stack model dot pop 2. Does that work? Is that a thing? No, apparently not. Yeah, no. Maybe that should be a thing. That's list. Yeah, oops. Let's also add a pop end method. Yeah. Pop on to called pop on list with only if list len is smaller than n, well then the len is list len minus n. Perfect. And list, oh yeah, no, that doesn't return anything. Nope, nope. Okay, so stack model.pop 2. Same, by the way, for subtracting, dividing, mod and or XOR, compare and concat. Well, hang on. We can do a more general thing. We can just say was that like a instruction dot signature or something? Signature. Nope. Nope, apparently not. sad. Okay, I guess let's add them down here. Each of these pops 2 arguments, then crashes, then the instruction. Except crash, that only pops 1 argument. Yeah, signature is not a thing. I know. It's kind of sad. Okay, yeah, called pop2 on list with only 0 items. Okay, yeah, compiling this. Add ints 0 and 1. Expression, this is 2. Okay, so we're compiling a yogurt body with 2 parameters. Which means we should push them to the stack model. Compiling body. Yeah, the stack is this. That's cool. And compiling instruction number 2. Instruction, yogurt instruction is add ints. Add ints, yeah. That's correct. Oh, I think something down here is wrong. Oh yeah, no. Not instructions.pop. No. Stack model. Well. Crashed. Oh, no, it should emit a crash instruction instead of crashing the compiler. that's cool. Yeah, okay, there already is a crash instruction, so I guess that's fair. Run crashed, and then this message, so that we also have an idea of what's going on. Okay, whoa. Okay. This is certainly something. So we're running in a VM. We push several things in here, like 5 and 1. What is even going on here? Let me just look at the Plum code. Oh, okay. So some sort of okay, I don't really know what's going on here. Wait, 5 and 5 and 1, 5, 1, 2. Oh, wait, 1, 2, 3. Okay, I can see that. Oh yeah, we're calling. We are calling the main function with 5. So initially there is 5 on the stack, then this function creates 1, 2, 3. Perfect. This is not perfect. How is this handled? Oh yeah. Yeah, and here we also need to adjust the stack model. So stack model dot push arg. Yeah. One, two, three. Then we want to create a list. So we create references to those objects. We add the list function, like the list function. And then we call that function. Okay. So this is all in object number 26. But we don't really call the function, do we? No, we just say, hey, here's a function. We also need to call it like this. Okay. Yeah, okay, some error, but let's see. So we call this list create function. The list create function then, basically it gets put on the call stack here. We are inside another function. The outer function, the main function, is basically stuck at instruction 8 because it's waiting for the inner function to complete. And the list function, it basically just creates the rest for the linked list. So a function containing 2 and 3, which means it pushes 2 and 3 to the stack, then pushes this other function, list create function for two arguments. Yeah. That function is then, it's this function's turn. This then calls list, please create a list of this 3. That function gets called, and that then calls, it just says here's an empty list, which is completely fine. Yeah. And then what is going on here? Let's maybe look at several things. The tag first. So yeah, this is very similar to calls, and it contains the same error that we did down here, that we don't adjust the stack model sufficiently. So stack model dot push arg. Then we push this, which basically pops all of the arguments. So stack model dot pop this number of arguments. Also, printing tags is not perfect. Yeah. Here we want to print a space between values. Yeah, something like this. Okay, so we create an empty list. Sure. Then we do something, and we call want to put, so we created an empty list, and now we want to put that into a new list. So we push the 3, we push the empty symbol, and then we combine those into this, into a more symbol. That is pretty cool, right? And that then, okay, we add another reference to that, call some function. Not sure what's going on here, to be honest. Should we start with a simpler example? Perhaps. But yeah, I'll try to understand this first. Okay, so creating a tag, let's maybe take another look at that. Okay, so we push all of the arguments of the tag, and then we push this tag instruction. Which I think works. So for example, this tag instruction takes the 3 and the empty, and it consumes both of them, and instead puts this on the stack, a more tag with 3 and empty as payloads, as arguments. Then there is, let's maybe look at the Plum code as well. So getting the length of this, or first creating this list, basically means we do this. And I think this works. We create a more thing. Okay, I see. Now we want to return from that function. So what we do is we push that again, yeah, and then we want to pop all of the locals below that. We pop all the locals below. But we don't do that. No. Okay, you know what? Let's maybe print the instructions that we actually execute. I think that would make things easier. Running instruction. Okay. Yeah, here we say, hey, please create a tag. Symbol more, consume 2 things, and it consumes 2 things, pushes a tag. Push from stack, yes, that makes sense. Push object. But why? Still in the same function. Would have thought that we return at some point, you know? But okay, we push some other function. We call that function. Okay, for even better debugging, let's just give our function object a name. And also function object should contain bytecode or other instructions, which is this, and it has a name. Yeah. Do we want the? Yeah. I guess it makes sense to do the same for the tag. It is more readable, so. Yeah, this is a tag object. Very cool. And then down here for the tag, we can just say, hey, tag dot symbol. What? That's actually readable. And tag dot args. Crazy. For functions, we can actually write the name. And yeah, we need to make sure when we create them that we don't do silly stuff. So yeah, instructions is this dot instructions. Perfect. And in here we have the tag dot symbol instead of dot a, because that's readable. Oh, right. Yeah, so tag object, I guess. But again, that's fine. Tag.args is this. We have, yeah, down here we also create a tag object where the args are this empty slice and the symbol is this. Actually readable code. Crazy concept. Yeah, there will be like several errors in here, because in here we actually want to create a tag object with a symbol and with args, like this. Of course, up here as well. Yeah, function.toInstructions. I see. Maybe to object even. Like, why not? Why not? And it just returns an object ID. Yeah, we do have the instructions, we have the name, so we can just do vm.new object.function. So object.function of function object with a name being the fun name or signature or something like that. And yeah, instructions being this. Well, not quite. Okay. Ooh, we don't know the... Really? We don't know the... Ooh. Why not? Hey, hang on, what is this? Oh yeah, to object. Let's get the name of the signature. Let's just pass that in here. And then in here we can use the signature as the name. And in here just say oh yeah. Should not push a new object. Instead just create a function and object.fun. Yeah, maybe do it like this. Okay, yeah, this does not work because we want a yogurt signature. I mean, sure. As long as we can just take the string down here. And it's not working. It is a still. Well. Oh yeah, this returns a function object. Okay. Oh yeah, when writing the stack in here, we'll write, yeah, the call stack. We can just write call the function dot get function dot name, something like this, perhaps. Debug. I'm not sure. Oh yeah, this is guaranteed to be a function. Ooh, what's going on here? Yeah, when printing the VM, let's actually print an empty line before that. And the call stack is pretty complicated now, so let's maybe print these on like multiple lines. And maybe indent it as well, because why not? Yeah. Okay. Whew. We see some things. Whoa. This is definitely something. Sure. So we're running a call instruction, so now we call the list constructor. Sure, that contains other code and calls something else. It calls the list constructor taking 2 arguments. Yeah, that calls the list constructor taking 1 argument, which creates this beautiful symbol, then pushes that, and then pushes something and calls that. What? What? What's going on here? What? Oh, so we do a cast. Oh, I see. Okay, I guess. Yeah. Then we have the cast. Yeah, which casts something. Oh, well, yeah. And that crashes somewhere. I'm gonna take a break. Okay, so I do have an idea where the error could be. Basically, I think when returning from a function, we don't clean that up properly. Maybe. I mean, yeah, let's let's look at what's actually happening here. So we have you know, some value here, and we want to cast that. So far so good. So we push this cast function and call that, and then the cast function wants to convert that to you know, from this concrete type to this more generic linked list type, which means that it's going to switch on that, which means pushing that onto the stack another time. Then it jumps on that with this beautiful jump table with only one entry, because this is only ever the more variant. So it does that. Then we add some other instruction. Then we want to untag that, which means this more thing gets kind of like unwrapped, untagged, you know. So only 3 and empty remain on the stack. And then we first convert those. So the 3 gets converted, so we push the 3 to the stack. Perfect. And then we want to call like the run instruction, you know, call the conversion function from int to int. So we push that to the stack. We call that. Yeah, we call that. So now let's convert this 3 to a 3. Yeah, basically we just push the 3, and then we return, which means we pop n below the top, and we pop one value below the top value. So this is the top value, and this is the local 3, which is no longer needed. Yeah, so basically this 3 gets removed, and the 3 is now cast to an int. Then we want to convert this empty thing from the type empty to the type linked list. So we want to push that to the stack, and here things go wrong. Like here we say push from stack 2, although it should really be pushed from stack 1. So somehow after the push, like pop n below top, yeah, this, yeah, I think we need to adjust the stack model here. So stack model dot find stack model dot pop n, just dot pop, like this perhaps. Okay, so compiling some body. Yeah, this is when compiling a body. Fair enough. Just want to look at the switch. Okay, well. Okay, so we have a body containing 0 and 1 as parameters. So the stack is this. Makes sense. Instruction add ints. This is the stack. Called pop3 on a list with only one item. Why? Where compile to I'm not sure what's going on here. Oh, hang on. For these, oh yeah, we need to push the arguments to the stack here. Similar to what we do for calls, for example. Yeah, exactly this. Yeah, let's use these here. Yeah. Okay. Okay, so there's something, definitely something happening. But what? Is there like a better non-debug version of this that would be useful? Nope. Nope, write yogurt body doesn't work. You can kind of like write the yogurt body, yeah, with a yogurt fun and int, like indentation. I mean, I'm fine with that. The body, like the body with the fun indentation 0. Something like this, perhaps. Yogurt body and yogurt op, but not expressions. Okay, I mean, I guess that's fine. Sure. Okay, compiling to bytecode. We compile a body that is this 0, 1, and it creates a 2. So we compile this instruction 2, the stack is 0, 1, which means then we compile some sort of body. Oh yeah, that worked apparently. So here's another body. Stack is 0, 1, 2. Here are some instructions, 3, blah, blah, blah. Okay, let's see what the surrounding body was. Compiling body. Oh, okay, so we have some sort of switch in here. Yeah, here, compiling body. 0, 1. Okay, so then in here we say call this built-in compares thing, and let's see how those are compiled. So first, the stack only contains 0 and 1. Then the 2 gets, like, you know, we call this built-in thing. Oh, I see. Yeah, no, these should not be there. So we do this. Wait, but we do pop them here. That's interesting. Those instruct, like, we push them. Yeah, I'm just realizing this could just be in more general, popping the popping this thing. So we could just say stack model dot pop this many instructions, please. So I am wondering how this works. So we are compiling instruction number 2. The stack is this. That makes sense, I think. We are here compiling number 2, and like expression number 2, the stack contains 0 and 1. And then this is an instruction after all. Yeah, so we push the arguments. Makes sense. So we push 0 and 1. But then we also pop all of the arguments afterwards. Rather, we could do this. Yeah. Push some sort of instruction that will then pop arguments. So we do that here as well. Okay. Yeah. But why don't they get popped? Like prepared args for built-in instruction, and then we just print the stack model, because why not? Wait, there is no... It doesn't say that anywhere. Prepared args for built-in stuff. Okay. Well, okay, so here we just call that. Like this. Oh, I see what's going on, potentially. When we compile a call, yeah, we push arguments, then we call the function, and then we need to pop those arguments. Same for tag. Not sure if, yeah, here we do that. Weird. Okay, but this looks better at least, you know. Compiling this, our stack contains 0 and 1. Now our stack contains 0 and 1 and 2. Compiling this thing number 9, which means we switch on the 2. So we compile the case less. Yeah, we compile the body. Yeah, this body right here. So compiling number 3 just gets emitted. Compiling number 6, sure. Then compiling equal O, and here the enum is no longer there. So in a switch, up here, for these cases, we I see. Yeah, so pushing this instruction should actually also yeah, it should also push that to the stack model. So we have a push, and then a jump table, which jumps to some stuff in here. Yeah, here we just compile the case. And what that means is we call this untag instruction, which then oh, I see. Yeah, this kind of replaces this this up here. Okay, so we don't actually need this. Yeah, just push untag, I guess. But then why is it here in that stack? Like, here we make some sort of switch. I get that. Yeah, makes sense. We want to switch on some value. But then we want to and we have this jump table, and then we basically consume the tag right here. Then in here, for the parameters, we push them onto the stack. We compile the value. Yeah. This will end up with a single instruction there, I think, that represents like a single item on the stack, which represents the result of that body. Yeah, this seems better. So we have this enum, and we switch on that. So we compile the case less with this body. So in this case, when compiling to compiling a body, this body, yeah, compiling 2, now compiling 9. This is the stack. Yeah, pushing, like popping something that doesn't make sense because we didn't push anything. Okay, yeah, compiling less with this. These are the local variables available. Makes sense. So we compile the 3. Boom, we compile the 6. Fantastic. But then we remove some other variable. That's not correct. definitely not correct. Is it just this down here? But I would have imagined that compile to instructions actually, that this results in let's just assert stuff. So here we have the stack model len. We compile something, and now now we assert that the length before equals the length after. Does that make sense? Like here we untag some stuff, we do this. Now we pop yeah. Oh, but no mismatch. That's good, I think. So compiling case less. But then it says compiling body with this, and then compiling case equal, and then compiling body with the 2 being consumed. What? Yeah, before the length was 3, now afterwards the length is 3. Perfect. So, everything's fine. Okay, then next case, compiling case. When did the stack length change between these? Oh, yeah. Yeah, okay. Compiling less to compiling 6, okay, yeah. And then what do we do in here? Down here we say, hey, pop all these. Oh, but we need to push body.returns. Okay. Yeah, some other stuff. Like I want to just make debugging a bit easier. printing strings is horrible right now because they are not quoted. Let's change that. Then what else? What else? Oh, these functions that get pushed onto the stack. They are also just weird. Let's debug that. I like, let's put quotes around them. Okay. Okay, so some non-unwrap thing, I guess. Sure. What is happening here? Let's maybe go through this one by one, and then we can see a bit better what's going on. Damn, this is long. Okay. Okay, so we're running something in the VM. Oh god. Yeah. We contain the 5 because that was our argument. We push 1 to 3. Then we want to call the list constructor, so we push the arguments to that. Also 1 to 3. And the list function, the list constructor function, we call that. So this should be replaced with a list. And then the list function runs. So it also prints like local variables 2 and 3. Creates this list constructor of 2 items that calls the list constructor of 1 item, only 3, and that creates the empty object and the 3, and then creates a more object, so more of 3 and empty. Yeah, then it wants to cast that, so it pushes that again, pushes the cast function, calls that, which means that we cast the int to an integer. Yeah, cast int to int. So we have this 3, and that gets casted to a 3. Then we want to cast the more thing to an empty. And I'm fine with this, yeah. Casting int to int. Okay, we're done with that. Now we're back here. We have casted the int to that. Oh yeah, now we want to cast the empty to a more thing. So we push the empty thingy, and now we have this cast empty to more. We call that perfect, and this should also, yeah, just return that. We are done switching, we return something, we are done with something and return that. We are done with casting this, so we return running push from stack. Oh yeah, so we are done, hang on. Oh yeah, so now we have cast that empty thing to an empty or more. I guess. Then we push the 1 from the stack, 3, and this. Oh yeah. Now we create this more thing, but of the new type. Beautiful. So here we have this mapped or cast more thing. We pop a lot of local variables, and now we have this successfully cast. We jump to somewhere there, push that as the end value, pop locals, these, boom, get removed. Okay, we have cast this. We return, push from that, pop locals, boom. Okay. We have created one list. Next, I'm creating the list with 2 items. So pushing the 2 to the stack and pushing this more thing to the stack, wrapping that in a more. Yeah, and then guess what? Casting that. So I'm not gonna go too much into this casting right now because that seems to work fine. But then this returns at some point, boom, and we're left with this. Beautiful, a linked list containing 2 and 3. And now we build the list containing 1, 2, 3. So we push the 1, we push this list containing 2 and 3, and then we tag them together into this thing. Nice. Then we want to cast that, with this cast function. So we call that, not going to go into the casting right now, because again, that seems to work. Yeah, and then we are here, we pop locals, and we are left with this. Boom, this one huge list. Then we are back in the main function. Okay, yeah, in the main function, we now want to get the length of the list. So we first push the list again here. Then the length function, we call that, which means inside of the length function we now jump on that. Oh, I see. And it's more, so we jump to instruction 7. Instruction 7 calls untag on this thing, on this, more of 1 and something else. So this gets untagged to 1 and more. And then we call push object, I guess. Okay. We get the length of the list, yeah. And we call something. Oh, I see. Yeah, we call ourselves recursively. Yeah, and again. And again. Yeah. This time with only this. So we call ourselves yet again. But now there's empty on the top of the stack. So here we jump to index number 2 instead of 7. And 2 is the one that returns. So here we push a 0 and then we pop back and jump to the ends of functions, pop things from the stack. We add things. Okay, I think that doesn't work correctly, but I'm not entirely sure. Oh, maybe it does. So length of something is just 1. Yeah, that seems fine to me. I don't know what's going on there, but sure. Yeah, removes local variables, and the length of something is only 2. Adding ins. Okay, this is interesting. So here we are done with the length calculation. So we remove items and we're back in the main function. where we now have the length in here. Okay, yeah, now we want to return a string, so we push hello world, there are, then 5, then the function toString of int. Oh, oh, this is gonna be horrible. Okay, so we compare int to 0. Yeah, that probably doesn't work. Oh, and that is actually where things fall apart. Interesting. Okay. But the length, the list length, that worked. That's pretty cool. Right, so calling this. Here we call that to a string of int. So that pushes a 0 and then calls something. So it wants to push the 5 and the 0 and run less than. So then we are in less than for 5 and 0. Yeah, 5 and 0, hang on. It compares them, like, oh, there's a greater, okay. Yeah, and here we are done with less than, and we end up with false. Perfectly fine. Then we run push from stack. And we jump on that. I see. So it's not less than 0. I see. So take this mod 10. I want to calculate that. Yeah, built-in mod. Sure. Guess what? That returns 5. Yeah. So far so good. Then push from stack. Wait, what? Push object 10 and 5. Okay. I think now we want to compare that to 0. So we push the 0. Oh yeah, so we first push 0. Yeah, then we push 5 and 0, ending up with this. Perfect. Then we want to push the less than function or compare to function or something, but instead we push a 0. That's weird. Okay, so let me. Yeah, I think there is something even simpler we can do. Let's say the call instruction directly contains the object ID, like the function that is being called. And in the when we have a call, now we don't pop the function, but instead we just call that directly like this. Yeah, this is a bit cleaner, I think, and also a lot easier. And like both here it's easier, but also in the code generation. When we have a call, yeah, we don't need to push this object. We can just say, hey, call this function. And it's not like we are any less flexible because of that. Oh yeah, I should put the, when printing the call instruction, it should print call dot function name something. Okay, yeah. And let's also, like, I don't have an idea why it's crashing, so now I'm just refactoring things and things that make sense to do anyway. Like, I think renaming this to VM is a bit better, because the VM is like the main thing that's in there. The bytecode sure is the the data that the VM operates on, but the VM is the main part. Byte code. Nice. So yeah, we don't have this. That's running in VM. Yeah, let's also print this like Ooh. I'm just realizing our VM is kind of breaks garbage collection, because we can have recursive functions, and those functions end up as function objects, which are recursive. You know, like one function object references another one, and the first one references the second one. Yeah. Because source code can be kind of circular dependencies. It's just that if you compile some source code, and then during runtime you compile new code, then the previously compiled code can't depend on the new code. So I think let's maybe let's rename this from, like, have one object that represents all functions of a single compilation unit, maybe. Yeah, let's call it code, and this will be a code object with functions. Yeah. Yeah. A code object with a I mean, sure. For now, let's just say it has a list of functions, like code function, function code. Yeah, function code is cool, I think. And the function code is just, it has these things. a name of the function and the instructions. Okay, and this code object, okay, is here, so the call stack entry then contains the code object, a function index, and an instruction index. Yeah. And also, we could have a separate struct for, you know, like the universe of objects, basically. And while you are running a single function, we have a data stack and call stack. So let's maybe call it universe of objects. And the VM then has a universe and these stacks. Okay. Yeah, that makes sense to me. Cool. Yeah, call doesn't need an object ID now. Instead, like, this is something in the code. And you can only call functions from the same compilation unit. We don't have closures yet. Closures will be a bit different, but yeah. And that means that this call will actually just contain like a function index. Yeah, easy. Yeah, you know what? You know what? I think as long as we don't have a compile function yet, it doesn't make a lot of sense to have this. No, I'm gonna leave it for now. Okay. Yeah. So we have a universe. Cool. The last expression doesn't match the return type. Indeed, because a universe has no options right now. Oh. Yeah, this is not really a thing, creating a VM like that. Instead, I think the call function should work on a universe. We could call this objects. We could just call this objects. Nah, universe is fine. Bit cooler. Yeah, something like this, perhaps. Yeah, but oh yeah, I think the new function should really be on the on the universe. Yeah. Yeah. Yeah, you shouldn't really create object IDs yourself, so I'm just gonna deprecate that. Okay, and you can get an object using an ID. So far, so good. Beautiful, honestly. Very, very nice. Okay. The VM, universe, and bytecode. Yeah, all Plum objects live in a universe. Basically a heap, basically that all Plum objects live in a are owned by a universe. Yeah. All Plum objects, yeah, including source. First, you create a universe using the Big Bang function. That would be pretty cool. Let's do that. Only then can you compile code. Into that universe. You can then call call compiled functions there. Internally runs a stack-based VM that interprets virtual machine. Yeah, compiled code lives in the VM as function objects. Hang on. Yeah. Converted into instructions for stack-based virtual machine. Something like a mini computer implemented in software. VM has its own stack data and call stack and operates on instructions for bytecode. Yeah. Okay, cool. So we have the universe. Which is a list of objects. And let's actually put the objects, boom, up here. And the bytecode instructions as well. Because those are the important things. Those are the API. You know? And then the VM is more like an implementation detail down here. Cool. So you can create a new universe. Yeah, you can create new values there. You can get values. You can print the universe, I think. Yeah, you should be able to do that. Well, currently you can't. Too bad. Should you be able to? Yeah, let's do that. Let's move this here. Let's have some sort of write method for the universe. That can write an object ID using this universe. Yep, ints should get printed, strings as well, tags as well. Yeah, sure. And functions just have, maybe do like function, and then we don't need the debug, I think. Very nice. Then let's print a universe. So this will just go over all of the objects, I think. Yeah. Universe, and then yeah, I do want to print the index as well. So I think the index will be like a hashtag maybe, just so we have something something new in here, like a new symbol. Yeah, hashtag object dot index colon and then the actual object item. Object.item, but that gets printed using the universe. Yeah, okay. And then the question is, how do we print objects? And how do we print bytecode? And we do that up here. Yeah. So printing a universe just prints the objects, and we have a way to print instructions as well. Oh yeah, we don't have functions really. We do have code. Yeah, yeah, we have code. With code. And this is really just it writes code, you know. So this will be like, this will never be on the stack. So we can choose. So I am going to choose a more elaborate representation for this. And basically just, you know, for fun in code.funs, it has the has the functions. Yeah. Yeah, and it just prints the function's name. And then for each instruction in fun dot instructions, yeah, nice. These are enumerated, yeah. We write down the index, so instruction dot index and instruction dot item, and maybe pad this to like 3 characters so that they are aligned. Yeah, also print like new lines in front of them, and yeah, here as well. Okay. And now we should be able to, I know, like there are definitely errors, yeah. Okay, so we have a VM. We can create a new VM, and a new object in the VM, true. And we can also get an object from the VM. Which is just VM.universe.get. Similar to how this is just universe.new. Okay. Oh, this is, oh yeah, this is correct. Dang. Yeah, you pass in the code and the function index and the arguments. Oh yes, it's a bit different. Yeah, object ID using the VM. That should work. Oh, using the universe. Yeah. Okay. Oh yeah, that's maybe make it so that you can just print an object ID. I think that would be cool.
and that will just print this. Yeah, just put the ID in there, that's fine. Here just the function, also fine. This is not a variant, indeed, maybe. Comptime. Oh yeah, it's push object. Oh, this wasn't used before. I see. Yeah. Mm-hmm. Okay. Code object, then we have the funds. Yeah. Does it make sense to have a separate like function ID? Probably, right? Probably. So this will just be an int. And then in here we just have the call. Another function from the same compilation unit. Beautiful. Yeah, you don't handle bytecode instruction dot tag. True. Ah, yeah. Add-ins, sub-ins. Divide, mod. What else? What else? strings. I know that crash is definitely built-in. Okay, so symbol is not a field on this. Oh. I thought this was replaced. Oh no, well, okay. Yeah, tag flip with this many arms. Beautiful, maybe, somewhat. Somewhat beautiful. Yeah, fun ID. You should be able to print that just by, you know, similar to this. And for the code, you also like print the function name in parentheses, and here we print the fun ID. So fun ID int is fun index. Or not. Right. Okay.
Whew. Okay. Call stack. We have the VM. We get the corresponding code. Yes. Then we say get the function. Oh, sorry, the fun index. Oh, hang on. No, this can just be fun ID, and this can just be fun. Okay, yeah. Mm-hmm. Yes, this does not exist yet. This should exist. Like, you should be able to, you know, given some code, and a function ID, you should get back a function, something like that, the fun code. Code dot funds dot get. Okay, yeah. Okay, so this is an object, but we know that it is code. Then this current call dot fun. Oh, dot code. That is definitely code. And then we take the function. So we get current call dot fun. And that function's instructions. Boo! Index is not a field in call stack entry. It's not okay, so it only contains these fields. Instruction entries. Oh. call that instruction index is something, yeah, vm.push object ID. Oh yeah, this should work. Wait, no, it should not. Should be mutable. Mutable. Like this. And similarly for the pops, instruction index. What? Yeah. Mm-hmm. Okay. Slowly but surely we do this. So we create a universe. We convert that over to bytecode. Let's compile this maybe. Yeah, should be something like this. And then we have a 5. And we say universe dot new. Mm-hmm. 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 Yeah, actually this is not returning a single object ID, I think. Or is it? Yeah, it does. Sure. Oh no, it does not. It returns a main fun, which for now is just code and a fun ID. And so this returns something. We'll figure that out. So yeah, this converts the function to that. Here we have the VM. Yeah, VM doesn't really exist, it's just universe. Yeah, like each VM, each lowercase VM in here will just be universe. And yeah, let's see what fails. Something definitely fails. Function object to object. Yeah, no, this returns. Oh, I see. this shouldn't. Yeah, this should just create function code, right? And that has the signature and instructions. Yeah, that's not an object, it's code. But yeah. Oh, never mind. What was it called? Oh, fun code. Sorry. Yeah, signature to ID, but that's not really. Functions don't map to an object ID, they map to a fun ID. The name signature to ID is totally fine. You know. And here this doesn't work because it needs a fun ID, and that should be it. Hang on, we have the body, we have instructions, yeah, we have the fun, the universe, this thing. Sure. Let's see, we have the body, instructions, stack model, fun, universe, signature to ID. Yeah. Oh yeah. Yeah, no, this is garbage. It's a placeholder object anyway, so let's just say fun ID int is -1. Placeholders. And this. Okay, so we compile this function to an object. And then we want to create, like in the end, we want to end up with a code object. So with this. Yeah. So let's just create that. Let's just say we have some sort of list. Calling it funds because why not? And yeah, we don't need to do this. Just compile that and that's perfect. Fun to object is also not really fitting. Let's just call it compile. Okay. Yeah, this doesn't make any sense. Instead, this should just do well, funds dot push or just literally this. Then we create that. Code is a new code object with the funds. Yeah, and then here we just return that. Yes, and this needs a main fun. Code. Perfect. Perfect. Yeah, let's just see what this does. things don't work. So, oh. Yeah, let's just say call accepts the main fun. Because why not? Code is not in scope. Indeed. This is fun dot code. Oh yeah. Dot ID. Okay, yeah. It does something. Compiling to bytecode. Okay. Ooh, -1. So apparently something. I know where that is coming from, but I just don't know why. Oh, I do know why. Okay, so up here we have this list of funds and we don't add anything to that, but we still get references. So I think we should really just push this compile function, and this works because iterating over functions is deterministic. Well. Okay, running. Let's actually like print the code. That should be interesting. Yeah. Main.code. Oh. We could just print the universe. I like that. Or maybe we can't. Maybe we can't. There's the signature. And the VM. There's some errors here. I hear. Indeed. Okay. So we have an object and a universe, and that doesn't do anything. That doesn't print anything, and it shouldn't need to be honest. I think this should just be the object. And yeah, printing an object ID works like this. Printing an object will not print, like deeply resolve the object. It will just do like a shadow thing. Actually, somehow something like this, I think, but different. Yeah. So I'm gonna call this, I don't know, write deep or something like that. Yeah. I'm gonna refactor this into a function like fun byte code, not fun code, but code object that just does this. Yeah, universe is not in scope, that is correct. This will just be the object. What about down here? Well, writing an ID. That should work, I think. Oh. Right, deep. Yeah. Okay. Damn. Well, instruction.index, that's true. String interpolation inside of string interpolation. Oh, yeah, but this looks cool. This looks pretty cool. This looks amazing. What? Okay. Okay. So we compiled stuff to bytecode. A lot of like false and true and hello things and so on. I mean, I guess, yeah. This is how the functions look. Adding two numbers like this expects two numbers on the stack, and it pushes top -1 and top -1. Basically duplicates the numbers, it adds them, pushes the result again, and then pops 3 below that. This constructor does some things. Oh yeah, let's look at the switch. Ooh. Okay, yeah, so jump 2 does this. Let's maybe add like 4, 5, 6, 7, 8, 9, 10 spaces before that. And I know it's like hard-coded in here, weird, but no, as long as it works. Oh yeah. Oh, amazing. So here we have these instructions. The len function that just jumps to... Yeah, let's maybe look at a function just to understand what it does. So this function accepts a single argument, which means that argument is on the top of the stack. And then we push that argument again, like we duplicate that. And then depending on what that is, we either jump to instruction number 2 or instruction number 7. So if this is empty, then we untag that, which means we consume that thing from the top of the stack, which we just duplicated, and push the payload, which is none. Then we push object number 99. Hang on. Which is 0. Amazing. Because for an empty list, it's like 0, the length is 0. Yeah, we duplicate that. So now there were 2 zeros on the stack. And we push the 0 below the top, so now there was only 1 0. And yeah, then we jump to instruction number 17, which means we duplicate that 0 again, and then we pop 2 below the top. Interesting. Why is that happening? Huh. To be honest, I am not sure why this is happening. Well, okay, I guess if this is more, then we go down here. We untag this, so we consume that enum and instead push the int and this the rest of the list. And we first push the rest of the list. Yeah. We call the fun -1. Nope. Nobody, nope. Nope. Bad. Yeah, to bytecode. Let's see. Signature to ID. Yeah, no, we should just put the fun code in there. Yeah, let's maybe do it like this. Let's say we get ref of the ID and that is the compiled function code. And then up here, rather than doing this, we just iterate over them and enumerate them. And so we have function.item.key, and this is the function.index. Len is not a field on this map. I guess not. I guess not. I think it just worked. Look at this, the call stack is something as the main, and then the main function returns, and this is on the data stack. Well, hello there. This is fantastic. What? This is crazy. This is crazy. Okay. Okay. What? Damn. Pretty cool, I have to admit. Pretty cool. Yeah. Wow. Very cool. Yeah. Yeah, let's maybe remove the debug print thing, like data stack. No, not this, but like the print lines. Yeah. So we run all of these instructions. We're just okay. It's kind of crazy, but it works. Nice. Very, very nice. Okay. Crazy. Crazy. Mm-hmm. What? Oh man. What? Okay. Pretty cool. Pretty cool. Mm-hmm. Man. Okay. Right. What to do now? Like, that was basically my plan for today. Compiled it to bytecode. Mm-hmm. Nope. Like, I'm gonna leave that here, comment it out, but you know. Oh yeah, and in here, oh yeah, there's this call thing, call function. Hang on. Fun call. Yeah, this should return something. It should return an object. Because after all of this, it should just, there should be one object on the data stack. Type data stack.len equals 1, or panic. Yeah, and then VM data stack get 0. Beautiful. Okay. Okay. This is pretty great. Mm-hmm. Yeah, let's use that here. So return value is this, and then we can say universe.get boom, and well, we can even just say standard output write deep of the return value, and this should print a nice stringified version of the value. What? Okay, so we don't depend on C anymore. We just compile to this bytecode, and then we run that. Mm-hmm. Yeah. Oh, there was this, like, compiling stuff. Yeah, for the yogurt things. Okay, yeah, stack length match, don't want that. Mm-hmm. Pretty cool. Yeah. Right. There are 5 arguments. Well, oh shit. Yeah. I think I'm gonna commit that. Hang on, just making sure that, yeah. Oh, hell yeah. Actually, I think I'll change how the code is organized into files. So I do like that currently every compiler stage just has its own file. And I think I want one file for bytecode. Yeah. So this will be something that contains this. Yeah. Yeah, I think I'm going to call this universe. I'm going to create a separate file for the VM, which is down here. Yeah. Bytecode in the universe of objects. Yeah, and this 2-byte code can then also just be moved into the universe thing. Well, all of this. Please don't copy the minuses. Okay. Mm-hmm. Yeah. So the compiler stages are still pretty simple. Mm-hmm. So here we have this
yogurt.compile into this universe. And then we can run that by calling this function. Perfect. And also, I think the VM doesn't really, like, hang on, let's first check if this still works. It probably will, because this was just, you know, shuffling code around in files. Restructure code, more files. And then I basically want, yeah, I thought about why not remove the VM. Because we basically have this one big call function. We could just as easily just, you know, everything is this function except for these few helper functions and the write function. We could just as easily also just save these as variables here. You know, data stack, call stack. And then here you can just say like data. We have two stacks, the data stack and the call stack. Hang on, before I do anything stupid. I mean, it doesn't hurt that it's its own like struct, and it does have a nice semantic, like a coherent semantic concept, you know. Yeah. And if at some point we want to, for example, execute code a limited number of instructions and then print something and then execute the rest, we can easily do that with a VM. So yeah, let's just leave the VM for now, and we can always refactor that later. Okay, so adjusting the comments. All Plum objects, including source code, are owned by a universe. First, you create a universe using the Big Bang function. Create an empty universe using the Big Bang function. Only then can you compile code into that universe. You can then call the compile function. Internally calling code, yeah. Basically this, and this is only universe and bytecode. The virtual machine. Internally calling code. Code runs in a stack-based virtual machine, something like a mini computer implemented in software. The VM has its own data and call stack. Data stack, yeah, and call stack, and operates on instructions called instructions called bytecode instructions. Yeah. Okay. Beautiful. I like that. Okay. The universe. And bytecode. Okay. Yeah.
think over time we will turn the VM into something lower level and lower level and lower level. So at some point, for example, we don't have objects. Instead, we will just have something like allocate memory, free memory, increase the reference count. We will have that in the instructions. We have separate instructions for that. Yeah, for now it's like pretty high level, and that's fine. Like it's at least easier for iterating on the language. Cool. Cool. Okay. To be honest, I really like how this looks now. How in the main function we just compile something over all of the compiler stages, and then we have this universe of values, of objects, and we compile something into that universe, get something back. If we want to call that with arguments, we create new arguments in that universe. And the return value is also something that we can inspect with and interact with. That's super cool. Yeah, it doesn't really make use of the static typing information that we have right now. So there is definitely improvement potential there. Yeah. Okay. But for now, yeah, update comments, I guess. Then, what next? There are two things that we still need for the compile function to work. We need functions or closures, and we need these like types as something like this, where a type is both a value in a signature and also used as like the return type or like a type. We need to add this to the function unification. Yeah, let's maybe do that first, right? Let's do that first. Yeah, okay. That should work in the yogurt when we look up functions. So here's this lookup. Oh. This lookup function, which currently only takes types. Although really it should take... Oh wait, no. Oh, yeah, that's fine. Yeah, looking up things should work based on types. Or should it? Like, okay, for example, let's say I have a function that takes a type and some value t, but the type is also named t, and it returns, I don't know, nothing. if I call foo int 5, that should match, but foo string 5 should not match. Right. Oh man. Yeah. So basically, I don't know why you would write a function like this, because you can always just remove this parameter. That's an idea. Yeah, just disallow functions where something is used both as a type and as like an explicit type, like a value thing in here. Because if you don't have this, then function overloading you can do function overloading just based on these types. Like if they are unrelated like this, you can, this still works. Like then both functions would match. Where a is int or string and t is int. Yeah. Hang on. Alright. I've decided that this is valid, but this won't be valid code. Yeah. Which means that looking up a function can only depend on the types of the parameters, of the arguments, it can't depend on the values. Okay. So we do need the values though to figure out the return type, because we might have something like this, a function that just takes a type and returns an instance of that type. So while this works, when we actually hang on, where do we calculate the return type? I know we do that somewhere, but yogurt stuff. To yogurt with a call. Okay. Yeah, we compile the arguments, sure. Look up a function, also nice. And now here, we look up the return type. Ooh, okay. So maybe it does make sense. For example, in this, we could match this function with concrete values, and then I could say, well, this function matches with the substitution t equals this type. So these functions, they have different t's. Yeah, I think that makes sense. Okay, so the lookup depends on the parameters after all. Which means this doesn't take arguments, which are Plum types, but instead it takes, something like, yeah, like this. Nope. Like this. It takes a slice of yogurt params And yogurt params can then either be runtime types or they can be comptime values. Okay, yeah, let's just do that. So lookup is in here. We'll look for a function with these, not Plum types, but yogurt params. Okay. And what we do is we match these substitutions. I think we can even like do one pass over the arguments, and if an argument is of the type, and then we just have put this name into scope and that's it. Because type is something like a special thing, like you can't, even if you have something like, I don't know, a list of type or something, in here you can't get the items of the list. So this really is only a constraint if this is invalid. You can only use type variables that have the type. You know, this is like, no, this has to be a type. So we know that we only if an argument has the type does it matter for the substitution and lookup and so on. Okay, so we have the name matches, and here we match them, like we match the arguments. I think we can just hang on, yeah, check that the number of parameters and arguments are the same. And here we have match against. Oh, that's interesting. Ooh, that is really interesting. Cool. It's probably one of these type functions, right? Yeah, map against. And here we have map against with concrete types. We have map again with slices of types. And both of them just call match against with a list. And check coherency. Right. That makes sense. Yeah, and here are the like actual implementations. Okay, I'm gonna remove these, I think. And this will probably result in an error here somewhere. Hopefully only here. Okay, and some other places as well. Oh yeah, this makes sense. Look up main with a runtime thing. So like yogurt param dot runtime type int. Because the int is only runtime known, and then down here where we say this, oh yeah, if we have some sort of call, then we compile the arguments. Arg params, these are yogurt params, oh look at that. And the arg types, we don't actually need them. We just use the arg params as well. Do we use the arg types anywhere else? I don't think so. So we can also remove them. Just use params for everything. Like this is pretty cool. And then substitutions is this. We are match against. That's inside of, oh, inside this. I'm gonna check that later. First I'm gonna check this lookup function. So, what we do is we create substitutions. Actually, I'm just checking, what did we do here? Constraints. And then this weird list. Oh, okay, that's... yeah, that is kind of weird, to be honest. Yeah, that's weird. Okay, so let's in the type. Let's just adjust these so that they also accept. Ooh. That they accept substitutions or like constraints. Yeah. And you can just, you know, give empty constraints in here if you want to. But we usually don't want to. Cool. So in here, substitutions is fun.params. Oh yeah, constraints is constraints, and then we can add a constraint somehow. Yeah, match against. Oh yeah, constraints.constraints.push. Let's add a function for that. Yeah. So if we have constraints, which are this, we can add a constraint which tells us, you know, name and type. And it just does, you know, constraints.constraints dot push a tuple from name to type. Very nice. So we can add constraints. Here we just say add this constraint. And over here, like for each of the fun.params do, yeah, if like fun.param no, if param is a args. Yeah, let's do it like this. So for each argument, if the argument is a comptime argument, as a comptime arg, then if its type is approximately equal, was it like this? I think so. I just don't know where the equal sign is anymore. Well, if this is the type, then we add a constraint. We add the constraint that that param, that param.name, the corresponding param, is okay. How do we do that? Zip the args and the function parameters. Like this. And then if the first one is a comptime argument, I do think it's kind of weird that this just returns substitutions directly. Well, anyways, yeah, then we add a constraint that the corresponding parameter name is the comptime value. Does that make sense? Does that make sense? This is not a variant of Plum type. What? If the argument is a comptime argument and its type is type, then we have an extra constraint that the fun.params. Where does fun come from? These are the egg funs. Hang on. Egg fun. Yeah, this is not enough information actually. We need we need the name of those parameters. Okay, so this will actually be an egg param, I guess, and an egg param as a name, which is a string, and also a source, because why not? And it's a type. Oh yeah, so the signature of built-ins, let's look at that. Returns a built-in signature, and yeah, let's maybe say these are egg params, because why not? Which means that yes, they need names. Ooh. Oh, I kind of hate this. Yeah, let's say they only take, but there will be built-in functions like compile where the name matters. Yeah. Yeah, these are egg params, I guess. But that means they need a source. Okay, you know what, let's at least say that these are normal strings and not strings and source code. So just some string. Okay, so here we can say, yeah, okay, we need a constructor for egg params. can we do like an @ symbol? Ooh. Yeah, no, that's would be kind of close. So a string and a type could result in an egg param with that name and type. So we could say, well, we have A, which is an int, something like this, you know, and B, which is an int, yeah. What's a good operator for that? Maybe this. Better than that, I think. No. Yeah, and I'm just gonna name all of these A and B. So A and B. Very cool. And concat strings. Yeah, these will also just be A and B. Oh, A and B. And crash. You know what? Let's call it message. And type info expects a type. Beautiful. And then in here we can say the params are actually egg params. And yeah, this param has a type. Does it also have a name? Probably, right? Of course it has. Okay. So that means that the egg now has function parameters with names. And that means that this works beautiful, and that this down here does not work. Okay, so the value is not a field. It has type and kind. Oh, right, because this is already unwrapped up here. That makes sense. This call doesn't work. Type variable constraints is what we want to add. These definitions have the same name, but arguments don't match. Add type variable constraint. Yeah. A Plum type. Oh. I see, because we know it's a type. We know that the kind is actually a type. Yeah. Okay. Very cool. Very, very cool. So then we have this. Egg param. Not quite. Oh, now we need the types of them. Well, okay. like this. So this is correct, but this is not correct. Ah, yeah. Yeah, something like this. Collect all of the types of the arguments and of the parameters, and then we match those. Oh, these are lists, of course. Match against Plum type. Okay, I think this should work. Oh, right, the constraints. Constraints like this. Or continue. Beautiful. And then down here, substitutions. I'm not sure how to deal with this. Like, I'm sure there's some way to do this more elegantly. To yogurt. We have these params. Oh. Yeah. I think we should just, instead of matching it again, we should perhaps use the substitutions. Which are just called substitutions. Well, yeah. So this lookup thing should contain substitutions. Like params result substitutions. Yeah. And then up here, substitutions equals something. Yeah, we don't need that. We only need this. It is kind of weird that they are like passed in from the outside. I think we wouldn't really need that. But then again, I don't know. Okay, so in type there is an error. Here. Constraints.add. Oh, right. No tuple needed. Look at that. Clean. That's the error. Okay, so printing a yogurt param doesn't work. Makes sense. In lookup. Do we print a yogurt param? I'm not sure where. Where do we print a yogurt param? Oh, here, probably. For the args, and args are yogurt params. Well, yes. So I think we can just say args dot args yogurt param. Just make it so that we can print yogurt params, right? And then things will work out somehow. That's my hope. So we print the param name and the param type. Oh, right, it can only be comptime or runtime node, so we switch on the param. If it's only runtime known, we just print the type. If it's comptime known, then we print the value and its type. Okay. Oh, what's going on now? Egg param. Of course. Yeah. Let's print egg params. We can print an egg, body, yeah, expression, sure. And between that also the params, which really just means printing the name and the type. Okay, now we get interesting errors. Oh yeah, the main function, when we compile that, we pass in these, but we also need to pass in the substitutions. So main.substitutions. Yes, that is indeed true, but it compiles. That's very nice. Actually, let's maybe, yeah, let's just remove this. Like let's paste it in here and adjust it. So I want a function that takes a t, which should be a type, and it takes a value, which should be a t. It returns an int because it always returns 0. So how about we call foo string hi. Ooh. Okay, there is no matching function named foo for the args string of type string and hi of type string. Interesting. Oh, right, this is an enum, not a type. Ooh. How about, oh no, never mind. Hello. Something like this. There is no function named type of. Well, there should be. How about, where are types? Lists, maybe we have strings. Yeah, let's maybe add types. Types. I think we can just have some type of function, which takes a type of type t and returns a type. Something like this should be built into the compiler. So this will call built-in type of with this value. Built-in type of with a value. Nice. What? Okay, let's first check out that this seems correct. This does not seem correct. Type of hello string returns -1. So let's maybe how does that work? How do built-ins get compiled? I think there's just a tyogurt with built-in, yeah. So we have parameters, sure. And then the return value is built-in.toYogurt with body and parameters. That's exactly this. And for the type of function, wait, what? Built-in type of? How does that not crash? What? Is there a type of function? There is not. why didn't that crash? Like, what in the egg? Honestly, why doesn't that crash? It just calls built-in type of, and that doesn't exist. I should fix that first. So here we go. It really just doesn't complain. Well, okay. So we have the egg where we convert things. Here we have a call of some name. Yeah, I should print the egg maybe. Instead of the yogurt, let's print the egg and see if that does work. Of course that doesn't work. This doesn't work, okay. Now it should work. Okay. Yeah. This is the egg, and this calls built-in type of that. That seems correct to me. Very nice. So the problem is when we convert the egg to yogurt. Here we convert an expression to yogurt, and that's a call down here, which means we compile the arguments of the call, I mean sure. Then we look up this thing, and that doesn't work. So this should return an error. Return error. Okay. And it really has a return in front of it, yeah. Return error. Yeah, let's maybe do that. Okay, so that is, never mind. yeah, this is what I want, but it isn't surfaced. Like it was just silently ignored the error. So somewhere across this call stack, somewhere where we call toYogurt, we just here we handle errors. Main fun, okay. Here we handle errors, yeah. We handle errors, we bubble up errors. Yeah, yeah. Okay. So maybe now it will work. Well, okay, yeah. Does it work now? Okay, yeah, it gives me a nice error with like underlining stuff and so on. Cool. Built-in type of. So let's now add this function. Type of, and we should add that here as well. Type of. Beautiful. Yeah, type of accepts a value of, oh, see, any type. So this will just be type T? I'm not sure. Yeah. Do we have something like that? I don't think so. Hang on, Plum type. Plum type dot yeah. Okay, Plum type dot primitive T. And it returns a type. Yeah, to do implement built-in type of. That's nice. Where's that? To yogurt and the yogurt. Yeah, we should remove this and just implement the things. So here, we get this thing. Yeah. The type is params.get. Sorry. Let's call it value, and then switch value is comptime. Value is value base type. If it's a runtime type, then it's just a type. Okay, and then we return this. Something very similar. Yogurt value type of this type. And ints. Yeah, that is important. I should handle that. And ints. Same for or. Again, for or, I think I need to call this or function. Right, and then there is XOR, which emits an XOR instruction, or it does this kind of thing, or does an XOR at compile time. Okay, yogurt ID is not an enum. True. This is a yogurt ID. Interesting. Makes sense. Yeah, I think this should be fine. Yogurt expression is not an enum. Well, hang on, does this have a type? Please have a type. Yes, this is a type. Oh, that's amazing. So I can just say value.type. Nice. Okay, this compiles. Nice. Very, very nice. I'm going to simplify this to something like hi. Yeah, it compiles type off, and then it compiles foo of type and hi, which is a string. Hang on, but this is a comptime type, right? This should be a comptime type. Yogurt value type to expression, and to expression and a yogurt value should just create a yogurt op comptime with that yogurt type. Yeah. Huh. I'm not entirely convinced that this is what I want. Why do I say like compiling with this? Just remove that. Oh yeah. It's the signature. Okay, so the yogurt signature. What does that do? If it's a comptime type, then there is definitely, it prints this. If it's a runtime thing, then it only prints the type. But that would mean that in here it compiles foo for a runtime type, which is weird, and which is exactly what I don't want. But why though? So we have a call. Basically we Okay, yeah, so let's maybe just print the yogurt and then I see what's going on there. Okay, so the main function, it has a comptime hello. Oh, I see. Yeah, it calls type of with hello. It has a comptime high, yeah. Then it calls foo. Yeah, with 2, which is this, and 3. So basically, should this call be replaced with I don't know, a comptime value? Maybe. Maybe it should. How does that work for other comptime known values? Like, I don't know if I add 2 and 3. The type of that is int probably, and not 5. Alright, because 5 is not a type. No, this is just int, and then this is... Oh yeah, the built-in int. Okay, this has a comptime. I see. And then this plus function, though, it doesn't have a comptime thing in here because it calls this built-in function. That makes sense? Yeah. So I think for a call, we could also see if, both arguments are comptime values. Then we make this call because it may have side effects like panicking. But we also, we don't use the result of that. And instead we immediately have a compile time known constant after that. And then, in later compiler stages, the call could then be optimized away and stuff like that. But future work. Okay, so yeah, we have a call. We look up a function, we convert that, we specialize the return type. Yes. Okay, so now we want the guarantee that if all arguments to a function are comptime known, then the function return value should also be comptime known. So basically, okay, the return type, we have that either way. Yeah, let's maybe for arg int arg params if it is runtime, then simple. Yeah, if all args comptime, then true. Else we just emit this call. And yeah, up here we basically want to emit that call, but then also emit a comptime thing of the result of that function. So this right here returns I'm not sure how to do that. I am not sure. Yeah, this calls that down here on the builder. Then we need to do this inside of the builder down here. Like instead of this returning yogurt expression, it returns a yogurt ID of the builder pushing something. Yeah, so then in here we can push this call, but then we actually evaluate to this comptime known value of this compiled function. And result.fun.toYogurt. That results in signature, I think. And then we can do compiler.yogurt.funds.get signature dot funds.get signature dot yogurt has funds dot get signature is the fun. Okay, and then we have compiled fun is this, and then we say compiled fun dot get compiled fun dot body dot returns, and we know that this will be an expression returned expression is that, and then we know that is some sort of yogurt expression which has an op, and we know that this is comptime. .op .comptime .unwrap, hopefully. Yeah. And then we have a comptime value of what the function returns. We do need to handle recursive calls of comptime functions. You know, if you have a function that, like if you guarantee that if you call a function with only comptime arguments, the result will also be known at comptime. And, you know, we treat it like a comptime value, basically. Then that means that another set of programs is valid or invalid than before. Because before you could just have a program that did, like, you know, a few functions known at comptime. All of the arguments are known at comptime. And a function calls itself recursively. Before, this was a completely valid program. You know, I don't know, I have this foo function which accepts an int, and the only thing it does is call foo with that same int. Before that was valid. This would just compile to, you know, a function that accepts maybe a comptime int, you know, a 5, for example, and then it returns an int. And only when you run the program would that actually like infinitely loop. Now we are changing this behavior. Now we're saying if all arguments to a function are known at compile time, then we guarantee that this function will be comptime evaluated, and that we will basically inline the value here. But that also means that for recursive functions, we don't want to crash our compiler, you know. So yeah, we somehow need to catch that. Like we do already catch that you know, when we realize, hey, we're compiling foo of 5 currently, and now we're compiling foo of 5 again, we will just return eagerly, even though we haven't compiled the function, because we know that the return value of that function will not be read. Yeah, so we put a placeholder in here. And the assumption was that recursive calls won't analyze the content of that function. They will only calculate the returned type. And this is not true anymore for functions with only comptime known arguments. So basically, if returns, for example, is -1, that would be a red flag. Oh, yeah, how do we do that? For a switch, for a call, we have the returned expression, which is this. If this is -1, then we return an error. A function with comptime known arguments calls itself. with only comptime known arguments calls itself with those same arguments. Yeah. We can't we can't compile this. We can't run this at comptime. Yeah, that's basically it. Okay. Yeah, so we do that now. I am very interested in how this is gonna look. This right here is an error, right? Oh, yeah. Well, okay, this doesn't work, so what? Compiler.yogurt.funds. Oh yeah. Yeah, this is, oh, signature. Oh, I see. To yogurt. This is, oh, this is a yogurt fund directly. Compiled fun, I guess. Sure. Yeah, we don't need this then. Yogurt ID and int. Yeah, and again, this is like pretty hacky. We may want to have a map with explicitly saying like, this is a placeholder, this is a valid function. Okay, so this is the signature, yogurt ID, error. These definitions have the same name, but arguments don't match. Oh yeah, this is a string. True. Like, we create an error. Oh, I think this needs, what is it? Needs a source. So I guess this is just export source. Oh, yes, 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 yes. Beautiful. Honestly, this is beautiful. Hang on, so before, back when, you know, back in here, main had the IDs 1 to 4, well, 0 to 4. 2, 3, a call, and a string. Now, though, it has, well, it has 1 to 5, but the 3 is missing. And there's a comptime thing here. Well, okay. So that's maybe, oh, I see why. I see why. When we compile the function, yeah. Here we just have this list of expressions. And we say, hey, you know, you want to add expressions to the body, just give the expression to us and we add that to the body and also add a mapping for that. But really, yeah, no, we don't need that. Um, Yeah. We could just give the expressions to this down here. Yeah, sure. So body will just be the list of yogurt IDs. And the mapping, well, yogurt code compiler, hang on. What was it, builder.push or something? Yeah, builder.push of the expression, and then also compiler.addMapping. Add mapping of the egg ID. Maybe not, but do expressions.push. And then also the ID. Oh, okay. To yogurt. Oh yeah, here we need to pass in the body, which will be our expressions. And we don't need this anymore. Yep. Wait, what? Oh, right. So now for the call, we can actually push the call itself, yeah. And then also use the here we should also add that to the body. So body dot push ID. Or just body dot push of builder dot push. Okay, yeah, look at this. So now we have a comptime known 2, a comptime known 3. We call plus with 2 and 3. But then we also use this, we create a comptime 5, just because we can. And the rest of the code now uses this comptime 5. And that means if we now call this this foo function, hang on, So what's going on here? We have a string comptime hello. We call type of hello. Yeah, but then, oh yes, here we have a comptime type, which is string. And then here, we call this foo function with comptime known type string and a comptime known value hi. This is pretty cool. This is pretty cool. Okay, yeah. Which means, look at this. A nice function body just returns 0. Well, but this now works. Whereas if you were to do this, for example, this should not work. Yes. Because now type of hello is string, and this is an int. And there is no matching function named foo for the arguments string of type and 5 of int. What? Because this function expects a t of type and then a value of that type t. I mean, that's pretty basic. So now we have overloading based not on types, but also on comptime values, which can only, like, the only comptime values that can affect the overloading are types, like first class type values, like these, but still, pretty nice. Okay, yeah, I should commit that, definitely. So we have a lot of things here. Like this is something separate, you know, implement int built-ins. We can commit that. Yeah, remove some of the logging stuff. It's also more like a general thing. Yeah, this is all overloading based on, values. Sure. Support overloading based on comptime values. Amazing. This is pretty cool, to be honest. This is pretty cool. Yeah, I'm gonna take a small break and then we'll see what we'll do. Okay, I'm gonna do something simple next. I'm gonna implement structs. So this will probably go through the compiler, but I think it won't be too complicated. What do I mean by structs? Well, let's look at some Plum code. The idea is basically that instead of something like this, with this OR symbol, you can also define something like, I don't know, person or human is an AND of a name and an age, for example. Something like this. And in a type context like this, this creates a struct type. And in your, in your normal code, you can write and name something like this, and this will just evaluate to a struct literal or something. And I think this will be pretty easy, because unlike with enums, where the type joining, for example, was pretty complicated, here we just, like, two structs are only compatible if they have the exact same fields, and yeah, and those fields like the types of those fields are compatible. So it should be pretty simple. And the logic of that is actually already, like, we already wrote that basically, because our enums, you can write an enum that is basically this, you know. But you can write this, and that's an enum human with only one variant, human, with a string and an age. So the only difference would be to have these like as named fields in here. Oh yeah, it would be also nice to, you know, if you have this, then basically say something like this. So we'll use the dot syntax for navigating into structs. Right. Okay. You know what, I'm gonna leave this here, and this will probably fail somewhere, and we'll just fix the places where it fails. So let's maybe also write some silly function, double age, takes a human, returns an int, and it's just human.age times 2. Yeah. And here we can do double age of me. Okay. So where does this fail? Probably somewhere in the parser. Yeah, expected expression. Okay. Yes. So let's just walk through the compiler pipeline. Starting at the bacon. So in the bacon, I think we need a separate handling for I think we have special handling for some of these lines that need an extra block. Here, create extra block. Yeah, for lines with a % or this. And now we're also going to add the end symbol. Maybe up here. Or maybe even, yeah, let's flip this around. Because usually when you talk about and or, you always say them in this order, not or and and. And the switch kind of only makes sense once you have these. Once you combine things, you can then break them apart again. Okay, so we have this check whether we should create an extra block, which means, does this look different? Expected expression, well, the error is more contained here, but apart from that, it's basically the same. Did we change something here? Interesting. Well, okay, next stage after bacon is the toast. That's down here. Do we want like single line ends? I'm not sure, maybe we do. Like, do we want, okay. Do we want to allow this, for example? Actually, I think so, yeah. Or maybe later, yeah. For now, I think for the or symbol, we also don't allow that right now. So let's just keep it consistent for now. Yeah. Cool. So converting bacon to toast. That happens in here. And we have this nice so like a to toast. Yeah, to toast of bacon. Beautiful. And
tries to turn it into a type definition or a function definition, and then these they call other stuff. So to toast type def calls parse type expression, which is defined here. Oh yeah, and here we see the special handling of if this is an enum, do something. Basically we want the same for is this a struct, then do something else. So else if this is, oh hang on, we can even, I'm gonna switch it, yeah, I'm gonna put the end up here, and this is the original. So then we're naming them fields. For field in bacon children, we create a parser, sure. Then we don't parse a symbol, but instead we parse name. I think that was the lowercase thing. Expected field name. And then we have the argument. First a colon here, so parser dot consume this, or return error, expected colon after field name. Yeah, and then there's the field value, which is actually the, okay, so if there were no, children, then we expect the value to be right there. There's only one type. Yeah. So just say type. Alright, and this is the type, not the value. Parse type. And then parser should be done. And we evaluate to the type. Right, otherwise we check that the parser is not done, that the field children to toast types, and we make sure that there is only one child, so child, or like children.len equals 1, or something is invalid. Fields can only have one type, and then we're gonna return children get 0. Amazing. Previous case to maybe toast type. Oh, so yeah, if there is no toast type, then expected type of field. Cool. And down here we then push the toast type field, I guess, with the name and the type. So toast type field, gotta add that. Toast type. Okay, so we have structs and we have enums. The struct is just a list of toast type fields. Yeah. Has a name, has a type. Simple. Yeah, fields.push and fields is defined up here as toast type fields. And then we return a struct with those fields. Okay. This should parse the type. Next, parsing the expression. So there is this, to toast expression inside of a function. We basically want to, we don't have this special casing of the pipe. Right. Yeah, so I think right here we check if parse struct. Oh, hang on, no. Yeah, if bacon dot line is just that, then we do other stuff. We say bacon to toast struct, something like that. So to toast struct on a bacon. Oh yeah, maybe this should just return a toast expression, I guess. And just check if the line is this, then stuff. Otherwise, if this is not that, then this is no match. If it is an end, then we want to parse the struct fields, similar to how we do that up here. So let's put that in here. And we have some fields, but these are just normal toast fields, not toast type fields. Let's see how that looks in here. Yeah, here we have a symbol. Name, switch, call. Yeah, put that here. Toast struct. Yeah, it just has a bunch of fields. We can also just put the fields in here, similar to this. So this will just be toast field. Beautiful. With a name and the value, which is a toast expression. So then in here, we look at the children. Yeah, we pass the name. Or if that doesn't work, then we say, instead of saying this, we say, hey, this was a bad input. Expected field name makes sense, then a colon, expect a colon after field name, then the value. And that's a parse expression. And hang on. If children is empty. Okay. Yeah. Right, then the value is parsing an expression, expected value of the field.
not sure how this. Oh. Yeah. But also in here we can, if we define a struct, then this should allow any type on that field. Yeah, like if a single field, hang on, in here, or if this is a huge thing like net from, like this for example, we want to allow that, but we also want to allow this, having like a complicated type with spaces there on a single line. And that means that we don't just want to pass a type atom, but really a type. Like type expression, I guess. Yeah. But not an atom, so. Yeah, okay. And in here we have this parser.parse. Yeah, if there is nothing, wait, a field of children is empty. So everything is, like this field is defined on a single line. Then we want the value of the field to be there. Yes, exactly. Otherwise, we want nothing to be there, correct? And then the children are converted to toast expressions. And there should only be one child. You can only have one value, we get the child. We get the value. And of course this is a toast field. And here we have something with the fields. Okay. Name is just a string. I see. Yeah, why not? Let's convert that to a string at source. Doesn't hurt, right? Try to create toast struct with list of toast field, but it expects list. Right, 556. To toast struct. Toast type. No, this should be a toast expression. Kind dot struct of, how does that work? Toast expression kind returns a toast. Oh yeah, with the at thing. Yeah, that makes sense. Alright. So toast expression kind at bacon.source.range. Bacon.source maybe? We have some very fancy, oh yeah, combining sources. You can just do that. So let's use that. Yeah, this will just be bacon.source until basically the last field. Which will be, sorry, not needed. Last field, and it's source, I guess. Yeah. It needs a slice. So this should be converted to a slice. Result maybe toast expression. Yeah, this can just return a parsed thing. Okay, then up here. Oh yeah, we can just do if bacon.toast struct is some expression, then return expression. And yeah, this can fail. Okay. We should be able to pass these. Yeah. So, well, maybe. Don't know yet. So in here, switching on a struct type. Yeah. We have a call, which is pretty complicated. We have enum. So what about a struct? Yeah, for now, just to do, and same down here. Switch, call. Oh, hang on, that was like here. Okay. Okay, let's see if this runs. Oh, additional gun. Oh, okay, but this is, you know, the next step, the navigating into, yeah, navigating into a struct. Yeah, sure, let's support that also right now, because like otherwise structs are pretty useless. Okay, so we have this parse type thing. We have the expressions. Yeah. And inside of the expressions, like not even inside of the expressions, but inside of the, you know, when parsing a single line, basically. Yeah, there's. I'm looking for the pipe, because on a single line we also support piping. We support doing this, for example, and I think the dot should be parsed like pretty similarly. Let's just maybe see where this occurs. Toast type, no, parse pipe. Guess. But this is the entire bacon. I wanna like consume pipe. Yeah. Okay, parse expression. Parse unpiped expression, yeah, okay. And then we repeatedly parse this pipe. Okay, yeah. Oh yeah, this is actually an atom, right? Yeah, because this expression doesn't include white space. Sure. Okay, if there's an opening paren, then sure. Blah 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 blah. We have these expressions. Actually no, let's first build some sort of initial expression. You know, something like this. Or if there is no if there is no opening parenthesis, then we try to do these things. This is kind of weird, but meh. Nah. Something like this. Oh, but also I don't want returns in here. Yeah, okay. So else return no match. And here we have an expression which we want to return, like parsed expression.
But before we do that, we want to loop. And basically do something quite similar to this. We try to consume a dot, and if there is a dot afterwards, then we pass a name, which will be the field name. Otherwise, this doesn't work because pass name. Yeah, sure. After the dot, there must be a field name, and then the expression just becomes not a piped call, but something similar. So how is piped call defined? Yes, something like that. So some kind of navigation. I don't know. I don't know if navigation is right. We could also call it struct access or member. Member is cool. And we access the member of something, of the struct. Or field. But that's kind of like toast field is already a thing. Yeah, let's leave it as member for now. Right. So this will just be the receiver will be an expression, like the expression that we currently have, and there are no arguments. No, there's only a field name. So member name is, well, sure, let's call it name. And then we take the expression source into the name source, something like this. And toast member doesn't exist currently, so why does it not show me an error? Because there is a more fundamental error without a source or something. There is no type in toast member. Well, okay. So type errors don't show up at types, that's weird. Here we have a struct with toast fields. A symbol. Yeah, I'm gonna reorder them. So we have the name, which is like very general, and then we have like ints and string, and structs and members. Like you're creating a struct, accessing a struct, creating an enum, accessing an enum, and then more complicated stuff down here. Sure. Yeah, I like that. I'll maybe move this even down here. Yeah, I don't know. Okay, member. Struct. Struct has fields, and then you can access those using a member. What is a member? Well, a member has an expression, which is a toast expression, and it has a name, which will be a string and source, perhaps. Toast member expression field is missing. Well, not anymore. Oh, but it has the wrong type. Yeah. Because we need to put that on the heap. And I hope name also contains the source. Okay, apparently it does. Very nice. Yeah, let's just see. Okay, yeah, in the egg we don't handle that. That's completely fair.
Yeah, I'm gonna move that down here. Just because it is kind of weird that it was between symbol and switch. Like symbol is, you know, creates an enum, switch matches on that. And yeah, here for structs, it's very similar. Okay, yeah, we have a to-do. Nice. That means that the toast was passed correctly. Cool. So the only thing we need to do is work on these to-dos here. Yeah, this converts. Yep, here we convert the toast type to a Plum type. I see. So our types, they also need to support structs, which will be map, I think, yes, from string to a single type. Each field can only have a single type. Oh yes, I see the errors already. Yeah, there's like the very naive equality checking. That's fine. Yeah. Well, sure. Do it like this. Oh yeah, printing a type. That's cool. So this will just be an AND. And then for each field of the fields, we just print the field. Field value is not, no, there is only one field value. Oh. Oh no. Oh, yeah, kind of like this, I think. Okay. Oh. Cool. Then down here, matching against the logic for matching. Match against, and here's the match against the logic. Yeah. So if we find a struct with generic fields, then we build concrete fields, which is the concrete thing which should be a struct, or it doesn't work. But they have to be exactly the same, so it's not quite as like in enums, you know. Like for each possible variant there can be, the type needs to match, yes, but also the variants need to, that their length needs to equal the other length. So yeah, for each field in the concrete fields we do concrete arg is field.value. Generic arg is generic fields get field.key or return false. And then concrete arg match against generic arg using the constraints and currently matching. Okay, perfect. But then we also do that the other way around. Oh, it just returns a bool. Okay, we could also just check the length. So for each generic field we check if it exists in the in the concrete fields, so that this contains the field's key, or if it doesn't, then we return false. Yeah, and if it is if it contains the key, then up here we have already checked that the types are compatible. Yeah, and like in the long term, we would print a nice error message here, like field doesn't exist or something. Okay, specializing fields. Well, for structs, it will be pretty similar to enums, I think. We just build fields, which will be a map from name to type. And then for each field in the struct, we check what is the value. And for, nope, there is only one value. And we say value dot specialize using that substitution. So this will be that. And then we push the fields. Okay. I think up here I also named it args, yeah, concrete. Yeah, why not? Cool. Down here, extend one level. Oh, this is interesting. Oh shit. Oh shit, oh shit, oh shit. Well, this can be complicated. So maybe first let's replace all variant with fields. Oh god. Yeah, in the end we create a struct. That's correct. We have new fields, which will be a map from string to Plum type. And for each field in the struct fields, we want to put something in this map. So far, so good. Yeah. Yeah, we only have a single argument, so we don't need to do this or this. We just say type equals. And we don't need this and this. We can just say, well, return that type. I see. Yeah. So if we extend the struct type, then we want to build this sort of extension. Yeah, that is the original struct, except the field that we navigate into. This field is replaced with a recursive type. That doesn't make any. Does that make sense? Yeah, I think. Okay, it does make sense. Yeah. Okay, so we have an extension with fields, and for each field that we want to extend, we put here something. Item. No, this will just be field.value. extend recursive types with this. Yeah. Crazy. Okay. Okay, yeah. This looks fine to me. So this, okay, I see. This will be the struct fields, where every field is in there. Okay, so this is this put. And the key is also always the same. And if it's the same key as the field that we're navigating into up here, then the type of that, which will just be one, the field value, yeah, this will just be this. Ooh, yeah, if they are the same, then it's going to be a recursive type, otherwise the extension field of value. I think that's it. Okay, then down here, when we actually expand that struct, let's see, we have Plum types in here. We don't need a list for this. We just take the field value dot extend. Yeah. Yeah, something like this. Okay, yeah. Then replace recursive level from int to int. What? But that is like a pretty mechanical thing, I think. So yeah. This will just create new fields, which will be Plum types. For each field we put a field in there, and this is the field value replaced. Yeah. And then next is equivalent logic. Okay, so this is actually pretty easy, I think. Okay, so we have a struct. The other thing also needs to be a struct, otherwise they are not equal, those types. They need to have the same number of fields. And for each field in the first struct, you know, the field has a type. So a type, and the B field has a type. So B field get maybe a field key or return false. Exactly. So it needs to be in the other struct as well. They don't have a length or name or something. It's just that a type needs to be B type. And that's it. So then joining structs. Yeah. Also pretty cool. So when we join structs, yeah, they need to have the exact same logic. So the exact same fields. Okay, so B needs to be a struct. We want to build some common fields, which will just be a map from this to this. Yeah, for each. Oh yeah, now we don't need to go over both fields because we can just check that they have the same keys. Which means that a fields.len equals b fields.len, or doesn't work. And then for a field, yeah, I think that's basically kind of this. So for a field and a fields, we get the key, we get the a type. Yeah. We get the corresponding b type, that's just b fields get maybe key, question mark. Does that work? I think so. Len is not a thing on right, so they need to have the same size. Also fine. Yeah, field is not in scope because this is the a field. Yeah, b field get maybe. Okay, only works on results. Look at that. Okay, yeah, if the struct b doesn't have the type, then joining doesn't work. And here we just put the fields in here with the, well, with basically this. We can remove this if because that the fields need to be in both structs. It's a single field, so we can just do join a type and b type. Hang on. Yeah. Okay. I think we implemented the type algorithms for structs. Pretty cool. So let's look back at the egg. No, at the toast. Also no errors. Wait, where did this? In the yogurt? What? Oh, wait, there were to-dos in here, right? There aren't any. Did we implement the toast already? Interesting. Okay, yeah, yogurt. Sure. There's only one place. Down here, type info. Oh yeah. If this is a struct, then we report the symbol struct and type info. Hang on. Yeah, this can also be a struct. Beautiful. Oh yeah, to egg. Oh yeah, we weren't even in the toast yet, so. Yeah, the egg. Yes. Oh yeah, we convert that to a Plum type. So, I mean, it will be pretty similar to this, right? Hopefully. We have fields, and then in the end we create a struct type using those fields. And the way we do that is we iterate over the struct fields, and then yeah, we just take the field, turn that to an egg. Yeah, we should do that, indeed. And we put that into the fields, like this. What? Pretty simple. Okay, so this doesn't work because hang on, the arg is no field type probably. Yeah, okay. Sure. Okay, next to do. To egg. So we have this, now we're inside a function body, and we want to create a struct. I mean, we're definitely going to push something. And there's this struct expression. It needs fields. It will be a map from the name to the egg ID, I think. And in the end, we will create that. Egg expression kind struct. Okay, so I think we haven't integrated that in here yet. Indeed, yeah, we have int and string, and then symbol and switch, but not struct. And member. Member of something, so of, I guess, and name will just be a string. Yeah, the struct will have fields. Oh, hang on, we could just, yeah, let's do that. Let's say struct. Ah, okay. Yeah, it has fields, sure, which have yeah, like this. Just have a map from string to egg ID. Okay, yeah. So yeah, hang on. First let me finish this. Yeah. Oh, hang on, we're in the types. Yeah, down here. A struct, field to egg ID, yeah, then for each field in the struct, we basically want to put the field name into the map with the key and the value being converted to an egg. Something like this. Key is not a field on toast field. Only contains these fields, name and value. Oh yeah, name and value. Even better. Check for duplicates. We should do that. Yeah. Then I think this is done. This doesn't work because string and sorts is this, right? Yeah, let's just turn that into a string. Perfect. Yeah, for member, the off will just be member dot, is it called off? I'm not sure. And yeah, then we push a new expression member which will be an egg member of, and it has a name. It's the member name. Beautiful. Yeah, member doesn't have off. What's it called in the toast? Member, toast member has an expression. Yeah, I like off more. Member of something, you know? Yes. Egg member. Oh yeah, this is just string. Sure. To just an egg ID to fill of egg ID. Oh, alright, because off is it's all IDs. No, yeah, okay. Makes sense. Yeah, here when we write the the order is weird. Int string, yeah, and now we have struct, which will actually be more similar to a switch, kind of, in that it has an end in here, I guess. Yeah, and then for each field in the struct, it just contains indentation and then the key and the value. Yeah, and for members, this is pretty simple. This is just member.off dot and then member.name. Oh yeah, struct underscore. Write, what's going on here? Yeah, egg ID, egg code, and int. I got like finding these. These are not sorted or anything. Yeah, egg ID. Oh yeah, makes sense. Like this is this is a complete body in here, but we don't have that. We just have a single thing. Okay, yeah, I like that. Let's see. Okay, now we're in the yogurt. So yeah, we have some stuff to do. So if there's a struct, then really we just want to, you know, like type check this and so on. But it's like, actually it's very similar to creating a symbol, I think. Not really. Similar to creating a tag, maybe. How does that work? Very similar to creating a tag, actually. Oh yeah, tag. Yeah, let's just copy this and see what we need to adjust. So yeah, we don't have a symbol, sure. Now we do have fields. Yeah, it's not really a list, it's rather a map from a string to yogurt ID. And we have, well, types, which will, yeah, let's call them field types, perhaps. Also a map from string to type. And for each field in the struct, we just look up the field the field value, get its type, and then we push the field itself into this fields and field types, and the type into the field types. Yeah, convert those to slices, and then boom, we have a yogurt struct. Yeah. Maybe even like this, yogurt.struct. Just with the fields, and this will be this with field types. Okay, creating a struct of the type, of a struct type. Yeah, member. This will be somewhat similar to a switch. Not really, because we don't need to join types or do like common complicated things, you know. But like, you know, let me compile this and strip things down. Okay, so the off is just the member of. Yeah, we have the off expression. Looked for member on non-struct. So this is expected to be a struct. We extend the type 1 level, also correct. Yeah. Yeah, we don't need to do this, or this, or this. Like this is weird anyway. We don't need to do this, or this, or this. Just return yogurt dot member yogurt member of name and field type. This is of type dot of fields, and then the field type is of fields dot get maybe of this member name, or if that doesn't exist, then that's actually like a pretty cool thing. We can say member.name doesn't exist. Yeah, then here just the, I guess, field type, like field of fields dot keys dot to list. Yeah, that's what I want. Just list all the keys that exist on the struct. Okay. Yeah, okay, so this doesn't work because this will be a put field key. Oh, well. The field itself isn't actually used anywhere but here, so I'm just gonna do that. Wait, it is field expression, I guess. Field ID. I don't know. Well, okay. Yeah, no, this doesn't make any sense. Cool. Alright, so yogurt also needs new operations. We have param uninitialized comptime, and then we have the order is weird. Tag to create a tag, switch to switch on it. Similarly, struct to create an enum, which will be this, and member to navigate into that. Yeah. And then down here we print that, possibly. Nope, we don't. We don't. Oh, keys. Yeah, okay. Maybe not. Maybe not. Sure. Name. Oh yeah, it's member dot name, of course. Yeah, we used that here as well. Okay. Yeah. Now printing these is. Of course, we need to do that. So let's maybe move that up there. Case struct. Yeah, actually just the end, and then for each field in the struct, we print field key is field value. And then for getting the member of a struct, we can just, we just print member.of.member name like this. Okay, yeah. You don't handle yogurt obstruct. Oh, not here, but in the, oh hell yeah, in the universe. Crazy. So we can tag something, we can untag something. Yeah, I think we just have a struct instruction for now. Kind of silly, but I mean, what are you gonna do, right? Oh, yeah, I think this will have a list of strings, basically. Pops the number of the same number of values and pushes a struct. And then there's member with a comptime known string, pops the struct, pushes its member to give a name. Yeah, yogurt obstruct. Hang on. Yeah, should do that. Again, I'm just gonna move the tag before the switch, just because I think that makes sense. And then case struct. Yeah, basically just we need to push the individual fields, similar to how we did that for the tag. Like this. Push from stack, find field, and then we also push the field there. Okay. And then after we've pushed all the fields, we then push the struct instruction, which just takes the names, right? fields is a list of strings. And first we just push, like we serialize these map keys into a list, like this. Right, and then we get the value. Okay, yeah, something like this. Don't handle yogurt up member. True. So if there is a member, alright, here we pushed all of these to the stack model. Now we also need to remove all of them, like we do here. Yeah, for member it just pops a single one and pushes this member instruction. With the name. Yeah. So we'll pop and ignore. Okay. Oh, hang on. The member of also gets like put in here. And then we don't need these. So off is we can just do this. Okay, member, and then instructions, push from stack, find distance from top of the member of thing. Okay. The VM also doesn't handle these new instructions, so we need to do that. Yeah, creating a struct. Hang on. With these fields. Yeah, let's call them field names. Yeah, for fields will be a map from string to some value, to an object ID, and we basically put here the yeah, we do something very similar to what we do down here. Num fields is field name is len. So then we have this field values, field names. Okay, so now we have field names and field values, and we can put them in here. And then create a new object. So basically do this. Yeah, vm.push vm.new object.struct with the fields. Perfect. And yeah, for the objects, we also need to, oh, that was in here. Yeah. Something like this. So in here we can this should just work. Then getting the member from struct. I mean, here we just take the struct basically. Hang on, it will be quite similar to this. Not really, but you know. So we have a struct which is just vm.pop that returns an ID which we can turn into an object like this. This needs to be a struct. Yeah. And then we get the corresponding the field. That's just this pop of VM pop stack. Okay, so yeah, mutable VM makes sense. True. This is directly the name that returns us an object ID, which we can then push to the VM. Yeah, let's maybe do it like this. Yes. Cool. Right deep. That's pretty deep in here. So, yeah, creating a struct, writing a struct is, yes, like very similar to what we do here, actually. You know, except we don't have a symbol, but we just put an and in there. And then for each field in the struct, we write an like a space and then the field. Oh yeah, space and the field key and then the field value. Okay. And the normal write was that? No, it doesn't exist yet. So we gotta add that too. Pretty similar, except we don't call write deep, we just do this. Perfect. You don't handle bytecode instruction.struct. Oh yeah, we're writing the instructions. Oh man. Yeah, creating a field name, struct with these field names. Yeah. Yeah, struct, and then with fields, and then for name and field names, we just put the name in there. Yeah. And there's also member. member, yeah, just member with a name. Okay. What? No more to-dos in here. Oh yeah, map doesn't exist. That's true. Yeah, let's fix that. Name is not a map. No, name is just a string. Oh, true. Let's comment this out, maybe. I guess also true. Although, that is kind of sad. Let's call them these. Ooh, look at this. Okay, so the type of this is wrong. This is I think the yogurt. Yeah, called double H, okay. Oh. We don't have the field access in here. Why not? Yogurt. Oh, hang on. Before we go to the yogurt, just... Yeah, there should be an equal sign here. So after we passed some expression, we then check is there a dot after that. And if so, we build a member expression, but we didn't actually use that. So of course, we have to take that as the new expression. And then try to pass another member and so on. I mean, yeah, this is pretty great. So double H takes a struct 0 and then gets the H 0.h as an int 2 and then calls this multiply thing. Damn. That is pretty cool, to be honest. Yo. Okay. Hang on, can I just, like, for example, return, not hi, but like me.name. Yeah, cool. I guess we have structs now. Okay, let's commit this. Yeah, we know we have structs and members. Struct and member here, like in the entire one tour through the entire compiler. And the type system as well, of course. And these, sure. Yeah, and here this. Nice. Support structs. I guess we now have structs. Okay, yeah. I'm gonna take a break. Cool. Yeah, next let's do something very simple. Like adding a result type. We have maybe here, so let's add result similar to like Rust results, you know. So result has an OK and an error variant. So it's either OK with that OK value or error with that error value. Right, so there is an unwrap method which takes the result of some OK and error, and it takes a message and it just returns the OK. Because if the result is OK with that OK thing, it just returns that. If it's error, oh nice, it can actually like, yeah, okay, this is fine, I guess. Yeah, I was thinking, could we maybe, you know, if the error is a string, could we maybe use that in the crash thing somehow? But I guess maybe later. Okay, so unwrap result OK error. Let's maybe do it a little bit. Let's use single letter things for types. That makes it a bit easier to see what's a type and what isn't. And again, like this is a limitation of the the language, you know, that there were only so many words and so much meaning you can put into a limited set of characters. Yeah. Okay, so here OK and error and no message, and this will just do this. Yeah, called unwrapped on error. Beautiful. Okay, let's just make sure that this this compiles. Very nice. Is there anything left to commit? Not really. Okay. Right. Next, maybe improve the type info built-in. So currently, oh, I can actually show that. Yeah, let's remove this the struct part. Okay, maybe not this one, but instead, let me write some sort of a function that accepts a type, which is a type, and it returns a string. So we're going to do type info on the type, and if it's an int, then colon, I think. Then we, was it colon for the switch? Yeah. If it's an int, then it's going to return int. If it's a string, then it's going to return string. Yeah, and let's see where this fails. Foo of type of me. Okay, so type info doesn't exist. Sure, I can fix that. Well, where's type of defined here? Yeah, type info of some type returns type info. What is type info? Well, type info is an enum. It's either int or string or struct or enum or type. I'm not actually sure about that, but I know we have the type. Yeah, this right here. So it's int or string or struct or enumod type. Yeah. Type info, cool. Yeah, let's just try to compile that and see if this works. Unknown reference name type info. Oh, yeah, type info of type. On type, that's not comptime. Like, that's basically not possible, right? Like, you can't. I mean, types are always known at compile time. That's the entire idea behind. Being able to generate efficient code depends on knowing types at compile time. So why doesn't this work? Here we call type info on this type. Yeah, okay. So here it already breaks down, I think. Here we call type info type of 3, and 3 is this struct. So type of, where was that defined? Type of value t. But this is the yogurt, right? Looks like the yogurt. Oh, maybe not. No, it's the egg. Okay, that explains that. Oh. Oh wait, no. Type info type. Type info colon type, that's not comptime. That's not possible. Okay, oh, yeah, this is helpful, I guess. Compiling built-in type of name age. Okay. Done compiling built-in type of name age. Done compiling type of name age. Compiling foo. Compiling type info type. Hang on. Let me think about this. Compiling type. Yeah, type of with this value. That makes sense. Compiling type foo and then type info. And then, you know what? I'm just not going to use that type and see what happens then. What if I do this? This should be... No, this is wrong. This should be... Oh, okay, so we call type of with this struct. Like this should be a comptime value, basically. Call type of with that struct. Okay, let's see. Type of is up. No, this is down here. Call built-in type of that struct. And that just is this comptime type. Oh. Yeah. Yeah. Before we kind of if you call a function and the value is not known at compile, like some of the arguments are not comptime known, then the result of the function call should also not be treated as being compile time known, even if it is.
if you call some function that takes 3 ints and only one of these ints is known, but the function has like a special handling for that first int, then you shouldn't just get true as a result instead of bool. You should only be able to rely on that being comptime known when all arguments are comptime known. But of course there's an exception to that, which is the built-in type of function. Yeah, okay, so I guess that makes sense. So we need to add an exception to a language. That feels wrong, to be honest, but sure. That was in the yogurt, I think. Hang on, case call, yeah. This one. Here we basically check are all args comptime true. Boom. And should be, or like comptime result is are all args comptime, or well, the name is built-in type of. Clean, definitely clean. Okay, so now built-in type of looks exactly the same, but type of now returns a comptime thing. And this right here, hang on, we create some struct, and then we call type of that struct, and we get back a type. Oh. Ooh. Okay, so it's not as easy as just saying is the called function type of. I'm actually not sure about what to do here. How can I do that? I mean, whether something is known at compile time or runtime is kind of... Is that irrelevant? Maybe a little bit. Like, could we, for example, say, if the last expression of this function is comptime, or if this function returns a comptime thing, can we then just treat this function as being comptime? Maybe.
Ooh, what to do here? What to do? What if a function? What is so bad again about seeing that a function evaluates to a comptime value and using that? I mean, sure, you're kind of depending on the internal behavior of the function, potentially. It does make it kind of impossible, or like less easy to grasp what recursive functions do. Oh yeah, that's gonna be. Ooh. Oh, recursive functions will be horrible. Horrible. Okay, you know what? Let's No, I'm not sure. I'm not sure about what to do. So I'm just gonna keep it as it is and think about this a bit more. And in here, just replace this with built-in type of me. Yeah. Let's see. Okay, so here we have a built-in type of me, and the type of that is actually a comptime known now. Okay, sure. I guess that's one way to do that. And now we can call foo with this comptime known type. Oh. Okay, so this is nice, I think. I mean, yeah, the underlining, like, that's horrible, but it's nice that, ooh, yeah, you switch on enum or string or type or int or struct, but you don't handle the enum variant, and indeed I don't. So maybe let's fix that. And if it's a struct, wait, this doesn't make any sense. We just return the string struct, and if it's an enum, then we return the string enum. Oh yeah, it can also be a type. In which case we just print type, I guess. Ooh, okay. Okay. So what do we do here? Converting something to yogurt? Oh, I'm pretty sure where this is. Pretty sure. Unwrap yogurt value? Really? Okay, this is probably here, right? Yeah. Ooh. I mean, is this kind of switch guaranteed to work at compile time if the value is compile time known? That is a difficult thing. I have no idea. Yeah, let's do that. Okay. So if we have a switch in here, then we compile all of the switch cases. Which I think is correct, yeah. Like for this we may want like an extra, maybe even a language feature, a new thing that tells the compiler, hey, please, this switch needs to be evaluated at compile time, and then the different branches are allowed to evaluate the different types, because then only the compile time, only one branch is actually compiled. Maybe that makes sense. I don't know. But what we can definitely do is if false, then yeah, we can lower all cases, I guess, and then find the common type of all branches. Sure. Yeah, first of all, I'm gonna remove this. Because this, I don't want this. You know, just because the condition of a switch is compile time known, doesn't mean that we don't want to get errors if there are mismatches in these types. Like by default, the language should be safe and branches should evaluate with the same type. I think we'll probably, I'm not even sure if it makes sense or if it's needed to have a compile time switch, but probably it does. But then we can still, I'm tending towards adding a separate language feature for that, for a comptime switch. Okay, so we lower all cases. And yeah, we just add cast expressions when necessary. True. Yeah, so we lower the cases. Oh yeah, yes. So here, I think, this is something that we can do. We can check, hey, is the expression comptime? And if so, then we do optimizations and do like constant folding in this branch, but with the with the correct type still. Oh, this is difficult. This is really difficult. How do we... Okay, I mean, this should work for now. right? It doesn't. Yogurt expression. Oh, what did it do? Nothing really. Oh. This should just be there, I think. Yeah, okay. Yeah. So if a value is compile time known, we should be able to rely on the fact that it is. You know, we should be able to just to evaluate the switch, but in a weird So we want to analyze all branches of the switch, but still only compile it if it's weird. Okay. Yeah, I guess let's not do this first of all, and that it's, and then here is dot up. Does that work? No. Okay, we can debug that. Nice. Okay. Could be should be comptime known, but it is switch. The condition is 2, probably comptime known. Yeah, and the cases or something. Yeah. Okay, so we have the common type. You got op.switch. I think if the I'm gonna remove that here because there's not like a bug fix or something. It is pretty obvious if this feature is missing, so like if that's something I need later on, I can always add that. Okay. Common type, add casts when necessary, I'm sure. And then, yeah, basically we want to, if the condition expression operation is comptime known, then here I have this yogurt body. Ooh, I think I know what to do. I think let's just take the yogurt body. So hang on. So cases get value dot kind, like variant is value dot kind dot enum dot like dot tag, I think, dot a, maybe. Then we get that. Like, this probably doesn't work, but or maybe it does. Seems weird. Yeah, then we push all of these to the builder, similar to what we did for the call. So here we have this yeah, here we have this body.push of builder.push of something. Okay, yeah, body.push of builder.push of for, I guess, ID in this do something. We already have the expressions, we just want to push them on the surrounding body. And then we want to return the last expression of that. Yeah, which is already cast to the common type. Perfect. Perfect. Yeah, let's call case body is this. And then case body that returns is the ID that we want to evaluate to. If it's not comptime known, then we just insert a switch with these cases. Does that work? Nope, it is not. What? Oh, what is going on here? I had that already. At some point, I think. It's a comptime value, it's a kind. Let's just take this and see what goes wrong. Okay, so this is a yogurt value kind. Does this have enum? Not a variant. Only has these. Okay, so it has tag. Yeah, tag on sure, I want to unwrap that. Unwrap.a. Okay. Yeah, the body has, I think, expressions like this. Not sure. Nope. Oh, it does. Okay. Oh, yeah, with the parameters we need to... Yeah, we need to assign those. And case body dot params do body dot push. Builder dot, what was it, push
yogurt_up.comptime. Basically unwrapping the thing right here, you know.
So this is a tag, yeah. And something like this. Yeah, these are like both things, and then we yeah, we kind of need to oh, all of this is kind of ugly, to be honest. The fact that we compile these bodies but then don't actually use them is kind of icky. Kind of icky. Oh. Yeah, for both in zip, we do body dot do this, and yeah, we basically want to create a new comptime value, which is a part of that value, but not really. We want to change the param thing in the builder. So the builder has expressions like this or something. I hope. Yeah, we basically want to get the A thing and replace that with a yogurt up comptime value of the actual like value in here of the tag argument. And then we do stuff. So we have a list and yeah, sure, do this. We can do that. Get ref. Oh yeah, it's a list and it's I see, we can do get, but that's not. This feels hacky. This feels very hacky. Don't like that. I don't like that at all. Okay, so the variable needs a yogurt expression. Well, it's a yogurt up. Which is different because what was an expression again? Oh, it was an op with a type. Oh yeah, so the type stays the same. Like this, kind of. Kind of like this. Okay, yeah, and then we push this now rewritten parameter to our body. Ooh, okay, yogurt expression, but previous case is the yogurt ID. Yeah, what's the correct thing to do here? I think, yeah, we do want. Okay, let's refactor this, maybe. Let's refactor this so this is not an expression but an ID, what we get back. So the individual cases, they need to push this to the body, to the builder and the body, let's say, themselves. So yeah, for this is kind of, it feels kind of verbose, but it is useful. Like this is, I think, clean. Because there are some cases that don't want to push something to the body directly. They want to give, you know, other code the option to do so. Okay, for structs, we just push that struct. For members, we push the member. Yeah, for switch, we do a lot of stuff. And then we push the switch. Then we have arguments, which, I mean, they are this, and these are that. Beautiful. And now, you know, here's a body push and builder push. And down here is also a body push and builder push. That makes sense to me. So then for tags, we do the same. Okay. Yield 478. Equals to nothing. To nothing. Body push. Oh, but because body push consumes this expression, kind of. Yeah, it does. Ooh. So I guess let's put that into a we could make body push return an expression, of course. We could, I don't know, like we need to return something from these cases and add that to the body. Yeah, we could maybe do this, keep the body push outside of that. Maybe, yeah, not super. Is that clean? I don't know. It's not ugly, at least. So that's something. Yeah, I know. Okay. Sure. So we have this. I'm fine with that. ID is not in scope. Well, what is call expression? Oh. Okay. Okay, so the code compiles. That is... Oh, that is new, right? Oh yes, that is new. Okay, built-in type of this struct is this. Boom. Comptime. Pretty cool. Built-in type info. Here's a struct. Like this. Hang on, type info on this type. Oh, hell yeah. Returns struct of this type. And then there is foo that just returns the comptime string struct. I love it. Okay, yeah, we have this working. So what I'm what I'm actually interested about was, what if type info was not just this, but what if type info also contained really like information about the type, like for a struct, which fields are on site. So this could contain a list of fields or something like that, where field is just has a name, which is a string, and has a type, which is a type. Yeah, let's maybe inline this. That's fine. And yeah, similarly for an enum, we could maybe show the variance, but it has a name and it has args, which is a list of types. Amazing. Yeah. And I think that this could be the the final form of type info. I don't think you need any more information about them. For an int, it's totally fine to just say, hey, it's an int. It's like, you know, you don't have any more information about the type. Strings, same. Structs, you know which fields there are. Enum, you know which variants there are. Type is if something is of the type, the entire like all types are known at compile time. That means that this type also, like, you can just inspect that type as type info on a type. Yeah, for now, let's just say this is a type. I don't think you need anything more than that. No. Okay. Yeah, later on we will add like functions or closures to this list, where you will probably have information about the signature, which will also be pretty cool. Yeah, let's just make sure that this parses. It won't compile, hopefully. It won't compile, okay. Yes, because the built-in type info function actually returns this instead of this. Cool. So let's fix that. Oh, hang on. Before I do that, commit things. Yeah, so yeah, I guess evaluate more things at compile time. seems fine. Now the type. Yeah, the type info type. I want to change that. So first of all, I probably want to add a type list function, which takes an item type, which is a Plum type, and it returns a Plum type as well. This already kind of feels like you know, like writing code in Plum. You know, you pass around types and you create functions that create new types and so on. Okay, so yeah, this really is just a Plum type .enum, which is either empty with nothing or more with something. And yeah, we have to put a list in here, a list of Plum types. So there is the item, of course, and then there is a Plum type dot recursive 1, I think. 1 above is the enum itself, yes. Yeah, there is no Plum type between this type and this type, so it refers to that enum. And then in here we can say, I don't know, structs. They have, oh yeah, by the way, this should be converted to a slice. Yeah, structs. They have a type in here. They have a type list of fields. Type field. Yeah, it's a Plum type dot struct with a map from name to type string and type to type. Yeah, and this is a list of fields. Perfect. Similar here. Yeah, variant is actually like the exact same thing. But, well, okay. Right. Now at least the okay, the types should match, but they don't. Why not? Oh, because, yeah, enums have multiple, not the same. See, this has multiple args, which is a list of types. A slice of these types. Oh, I see. It's a type list of types. Yeah. Oh. This is nice. This is nice. So in our code here, we don't capture these, and we should. So how about now? Yeah, I mean, this is expected, you know. Yeah, done compiling type info and then things don't work out because the type info doesn't return what it claims it returns. So let's fix that. Type info is down here. Oh, hell yeah. Okay, so yeah, this will actually be different. It will... Ooh, to be something like this. And I'm gonna inline this switch in here. And yeah, basically use this as the default thing, you know, for primitive types. We just say it's this. Hang on, the name is already a string, right? Isn't it? I think it is. Okay, never is never, struct is struct, but we should change this to some yogurt value, some crazy yogurt value. Yogurt value dot, hang on, is the yogurt value got something. Not yogurt op, right? Yogurt value kind probably. Yogurt, yeah, value kind dot tag of the type type list of a list of the type info. Oh yeah, so this can just be, I see. Yeah, this can just be a tag. That's fine. With nothing, this will probably not work. It needs a tuple of a string and a slice of yogurt values. Okay, so basically it tells us I'm a struct and I have this slice inside of me. Slice of yogurt value. Oh, this is amazing, because if this is a struct with fields, now we can actually like turn the fields into yogurt values. What? Now what was it? A struct of something? Or a slice of something? Slice of yogurt value. So this will be a yogurt struct. For each field in this struct, we want to push something to these fields. Yeah, what do we want to push? We want to push the yogurt value dot struct, which is the yogurt value kind struct, which contains things and has the type field. Yeah, which means it has a name, which will be the field name, and it has a type. Oh, which will be a type. Hang on. Yeah, let's say field type. This is not correct. Yeah, name is not a field on. Oh yeah, makes sense. Key and value. So these need to have the same type, and in particular, I think they need to be yogurt values themselves. So this will be a yogurt value kind dot string of the type string, and this yogurt value kind of the type. Does that make sense? I think it does. Hang on, what's going on here? Oh right, because operators are left to right. Makes sense. Small price to pay in order for to simplify the compiler and have less syntax and have this just defined in the standard library. So you got value kind. Yogurt value kind. Hang on, how do you create a yogurt value? Yogurt value has a Plum type and a yogurt value kind. Where like a yogurt value is, how's it created currently? Hang on. If we have a yogurt value, sure, we can turn that into a yogurt expression up here. Oh no. Oh no. Yeah, no, let's not do that. Let's instead say that we have this thing, which also takes a value kind, which is a yogurt value kind, and it takes a type, which is a Plum type, and it returns a yogurt value. Yeah, so you can actually just do this. Not call it kind, yeah. Then we can just remove this and maybe flip this around. Why not? And this right here will just be at type int. Look at that. How short and readable this becomes. Yeah. Yeah, but I can use these in some places. Symbol, right. So this will just be the yogurt value kind tag. Using the symbol, this. Beautiful. And down here we can simplify this. We can say yogurt value string and we can say yogurt value type. Nice. Yogurt value kind struct. Wait, what? Huh, we don't have comptime structs. Indeed, we don't. Interesting. we should have them. Yeah. Sure, printing them is yeah. Okay. So this doesn't work because we try to push something on a list, but it needs to be a reference of a list, like this. Sure. So this call doesn't work. Yogurt value symbol of yogurt value kind. That is indeed true. Should just be this. Yogurt value kind dot tag of a tuple containing a struct and some fields. Oh yeah, and this should of course be the type info, like this. Because of course. Yeah, something very similar for the enum. So here we have an enum with variants. Oh, let's call it enum. And then here we have variants. They contain arguments. And each variant has a name and arguments, which is a list containing all of the arguments. Hang on. I need to make sure that this makes sense. Okay. What do we do with the fields here? We put them in this tuple struct. Does this make sense? I don't think so. We never create any list here. Why does that still type check? Like this evaluates to a slice of yogurt values. Oh, which is oh yeah, that's correct. Yes, but of course we don't want a struct enum with an enum for each field. Well, instead this should have single value, a single argument, a single payload that is a list containing the fields. So we need a new type constructor up here. Where's that? Here. Yeah. Yogurt value list with some items, which is a slice of yogurt value, and this returns you something, a yogurt value. Let's just sure we have that much space here. So this is gonna be a tag. Hang on, we have the items. We need the items type. Yeah, type list of the item type. Perfect. And so its type will be yogurt value kind tag, correct? Of a tuple, also correct. But what's inside the tuple depends on the list. So if the list is empty, if item is empty, then this will be one thing, otherwise something else. So if this is empty, it's actually gonna create an empty tag, otherwise a more tag. The empty tag is no thing in here, like nothing, and the more tag has two things. It has a value, so items get 0. Hang on, let me switch this around. Get maybe 0 is some item, like this. Then we have a list of the item and the rest of the list converted to a yogurt list. So basically a recursive call to yogurt value list of items dot subslice from 1 to items dot len and the item type. What? Yeah, something like this. A list with 2 items. Yeah. Like the actual item and the rest of the list. Yes. Looks correct to me. So then in here we have this list, but what we actually want is a yogurt value list of that. So not just, you know, a Martinez list, but convert that into a list that is an actual list value in the user space program. Alright, so this doesn't work because this is the signature. Oh, slice of Plum type. Alright, because these are multiple types. And this is also gonna be a list. So yogurt value list of something, of the args, which are a list of yogurt values. And then for arg in variant.value do args.push. Yeah, this exactly. And then do this. Okay, this doesn't work because it expects a type, like type, a list of types. And unknown variant yogurt value type tag is what it is. And it's a tag with a list, a tuple, correct. Yeah, similar to this. No, hang on, what are we doing here? We have these, an enum, with variants, which are a list of yogurt values. That makes sense. And now we want to create a struct of this map. Hang on, let me just check this. So struct of map, and this is type variant, yes. This call doesn't work. Oh yeah, so this outer call needs to know which types are the variants inside. Why doesn't this complain? Struct, and it just... Oh, I think, oh, this is also wrong. Yeah. Okay, so the type of this hang on. Yeah, I guess. So this is a list of enum variants, yeah, type variant. But then of course this entire thing, exactly. Yeah, it has a single yogurt value, this list, but it actually needs a slice of them. So a list of this, ooh. Yeah, let's maybe not do this like this. Or maybe, yeah, I think this is fine, yeah. That's okay. Oh, shit. Look at this. Amazing. Yeah, this is also wrong, because this should be a struct with not like multiple payloads. No, it should always be a single payload that just happens to be a list. No, that doesn't make sense either. This should be here, and this also expects at the type field. List of fields. Okay, I think now, at last, phew, universe to object. So we added the struct value type. So yeah, type, we'll move that down. If something is a struct, then we just create a new struct, right? Like, okay, yeah, we gotta do this, like get the struct fields, and for each field in the struct, we actually do have to create a map from string to object IDs. So take the field, convert it, its value to an object, and put that into the map under its own key. And then we can create a struct with the fields that we just generated. Cool. It compiles. It compiles. It compiles. What am I looking at? Okay. What we call foo. Sure. So here is foo. Oh, look at this. So first of all, this is a call of type info. Makes perfect sense. Perfect sense. is it just the... I think the yogurt printing of comptime things is kind of broken. The value, yeah. And the value is a yogurt value down here. And if that is a tag, it just, let's add parentheses around that. Yeah, they are not necessary all the time, but often they are. Okay, so we have this foo function. We call type info of this type right here, you know, of the type. It's comptime known, it's this type. So it's a struct containing a name, which is a string, and an age, which is an int. And the type of, like the return type of type info is this. It tells us, well, it's either a struct with, you know, a list of fields, so structs containing names and types. This is this, yeah. Or it's a string, or it's a type, or it's an int, or it's an enum, which is then a list. So it's either, you know, an enum with something that's either empty or more, containing information about the enum variants, including name, which is a string, and the arguments, which again is another list inside of that. A list of types in this case. Crazy. This is crazy. Okay. So we call that, I mean, fair enough. And because this type is compile time known, because all types are compile time known, this is the type here, then we also have this comptime thing. The type is exactly the same as above. If I zoom out, yeah, this is even more obvious. Like, until here, both lines are basically the same. The difference is that in this second line, it is a comptime value. So it is very concretely a struct containing a list. Well, it contains a list of more of this thing, something with a name and a type string, and then another item, which is the rest of the list. And this contains the next field with the name age and the type int, and it's empty. Damn, this is cool. Okay, so hang on. Can I, if I, what if I, hang on, okay, I can do this. Okay, one thing. What about recursive types? Yeah. So what if I have instead of this, I just have, I don't know, list of 1. What's it gonna do? Oh yeah, this doesn't work. So I know. Oh, seems wrong. Okay, done compiling list 1. Okay, so there is this cast call, which is, yeah, like if we don't right, we cast something of this to that, and this is supposed to be comptime known. Yeah, it is, but it's not. Okay. Oh, I know why. Because we have some call. You know, if we find a call, and then we find out, hey, the call has a comptime result. The last value should be comptime known, just like it says here. But if we have, for example, a cast call, and switch. Yeah. Yeah, here we don't yeah, lower all cases. Right, so in this case, if the condition is comptime known, then the parameters should not be runtime parameters, but they should be comptime. Hang on, that makes... I remember I had this like... Wait, we had this super ugly code down here. Yeah, where we like mutate the references to be comptime. We can just do that inside of the switch, like inside of the... Oh, and then... Oh, this is great. This is so great. Okay, hang on. Switch with condition... Yeah, condition being compiler.lookup. Okay, there was lower all cases. And we have the params, sure. And for each argument we do something. And here we can basically check something. Like, sure, this is the default case, you know. But for the non-default case of our condition is... Our switch condition is compile time known. We do something else. If our condition is comptime known and it is exactly this condition, you know, and var our params const, yeah, and then if condition is comptime value, then sure, we have the variant like comptime yeah, something like this. If condition is what did I do? I deleted the cool thing. Up, what was it? Condition expression, yeah. Const params, maybe? Yeah, if this is comptime known value. Then we take the value, the kind, the tag. Yeah, this needs to be a tag. We unwrap that. And we check what is the variant. No, if this is our variant, you know, like a variant.key, then we take the parameters. Boom. Otherwise, we say nope. Value kind tag unwrap. Yeah, otherwise, nope, doesn't work. Const params, and that's like none yogurt value. Else none yogurt value, like list or like slice of yogurt value probably. Kind is not a field on tuple, only contains these things. Well, that's true. So let's do this. Does it? No, this doesn't fit. No, of course it doesn't. I mean, this is pretty readable, so. Yeah. So then in here, if const params is some const params, then we do crazy stuff. Otherwise, we just take runtime parameters. Okay, this is great. And in these cases, we just do something very similar actually. param.comptime, and this needs, oh yeah, and this needs hang on, can we just say params equals oh yeah, that's maybe even more elegant. I have the params here, and then do something like if it's comptime known and this is comptime known, then actually just replace them. So something like this. Look how short this code is suddenly. Okay, so then params is this. It's a list. It's a slice. Yeah. Do it like this. Sure. Invalid assign still, because needs slice of yogurt param. The value is a slice of yogurt value. Indeed. Indeed. Okay, I see that. I see that. Huh. Mm-hmm. Mm-hmm. I feel like there is some elegant way to do that. Slice of yogurt value. Yeah, I know. So I guess not do this after all. Yeah, comptime params is just a list of yogurt param, and for I mean, sure, let's just remove this and let's move that down here and let's just clear the list. Okay, params.clear, and then we push them again, but this time comptime. Yeah, why not? So we have params. For each param here, we push them, and if the condition is comptime known, and the value is our current variant, the case that we are currently compiling, then we'll actually clear the params, remove and overwrite them with our comptime params. Pretty amazing. Let's see how that works. Not well, apparently. Okay. Why not, though? Why not? I mean, we have this. Oh yeah, I think here we also just need to we replace this with a comptime known value. Yeah. Yeah, old body dot returns. Oh, yeah, casting can never fail, actually. Ooh, so we can just do if old body dot returns. And if that is, oh, that's an ID, right? So if, was it fun.get or something? Builder.get? I think builder.get old body returns. If that is comptime value, then stuff. Otherwise, this default stuff. The type will always be the same. Yeah, yogurt expression is not an enum, true. But if the operation is comptime,
And then we don't even like call this. We need compile time casts as well. Right. Yeah, this to do, like fix me, to do, comptime cast. This is very important. What is a call? Still that same thing. Okay. Okay, so for each case, we basically, if the types are not the same, then we push the new types and the new returns something. Wait a minute. Yeah, never mind. This doesn't make any sense what I'm writing here, I think. Yeah, I think this is just yeah, but this is not correct, I think. We still need a comptime cast here. Yeah, okay. Okay, but this is basically the new returns. View at body returns new returns. Yeah, exactly. Exactly this. Comptime cast, we need to do that. So I find it nice that like over time, basically the same to do accumulates there, like beautiful. Yeah, builder.push. What's going on there? I find this kind of weird, to be honest. The case expression is, for each case, we basically get what does it return. If that's a comptime value, then great. If not, then case expr dot debug is not comptime. No. which kind of surprises me, and like I think it's comptime known in a lot of cases. Like if it's true or false, you know, or the string or something. There's still the egg. No types in here. No types. Oh, it didn't compile. What case expression is not comptime known? And it says this cast. So we need a cast. We have the egg. It doesn't even say that. Wait, what? Where do we add casts if not in this? Oh, at the end of functions. I guess we do that. Oh yes, we do. Okay, so yeah, compiling a function. Where's that? Like to yogurt of function. I think here. I'll just compile the function and then in here say, hey, this is, we need a cast here. Yeah, I have this comment here because now we basically make this code wrong in a different way. Yeah, we'll just if body dot returns, well, hang on, if body dot this dot of is comptime value, then let's just assign that to the cast variable up here. That's pretty cool. That is actually pretty cool. Yeah. So here we just say, hey, we push this thing. Yeah, this is just yogurt of comptime. We don't need this, that can be this. Yeah. And the comptime thing will just have the value. Yeah, that's it. Like this. So there was a cast. Okay, of yogurt ID 2. Interesting. Interesting. So that means that the body return value was not comptime known. Oh. Hang on, the parent types.
actually needed. So, yeah. Body to yogurt with params. That basically does this. I think we need to handle comptime things differently. Yeah, params. I'm not sure about this one. Params.get to expression. Yogurt param to expression. Oh, okay, so this will be actually like a yogurt of comptime. That is nice. That's really nice. Alright, I guess. But value should be comptime known. But it's call, and then a yogurt call with a receiver casting more. Of end and something to empty. A cast thing. Yogurt op.call. Adding cast. Adding runtime cast at function end. At end of function. Mm-hmm. Yeah, okay. So a tag always results in a tag operation, which we also don't want. Instead, if the arguments are comptime known, yeah, then that should just be a comptime thing. So if args dot all args comptime, is comptime, why not? That's true by default, yeah, and then we just iterate over the args. Is comptime, set that if arg, if builder.getArg is runtime, then is comptime equals false. Beautiful. What's going on here? Yogurt expression is not an enum, so this so if this is not, yeah, kind of like this. And then finally if is comptime. Or like put that in here perhaps. You know, if it's comptime, then it's just yogurt up.comptime of a yogurt yogurt value symbol, no, yogurt value tag. Well, yogurt value kind dot tag with a tuple of the symbol and the args. Comptime args is something. What do we do? Let's just say the maybe we do this, and then here we do something, otherwise we just emit a tag. And the type is always the same. Very cool. Yeah, let's put that up there. So then here we have this. Okay, so the only remaining question is what about this part right here? We have the symbol and we have the args. We know they are comptime, so comptime args. Let's just create that. This will be a slice, a list of yogurt values, and then for each arg and the args, we basically get a builder.get arg.up.comptime.unwrap, which gives us a value. And we push that to comptime args. And then we do comptime args, convert that to a slice. It needs a yogurt value, not just a value kind. Yeah, because this also has this type. Okay, so now tags should also happen at compile time. Maybe let's just quickly go through the other operations just to make sure that they make sense as well, and they don't. Okay, so int, yeah, that makes sense. Always comptime. String, always comptime. Symbol, always comptime. Sure. But now, struct. If all of the fields are comptime, we should, do all of that at comptime. So, is comptime, which should be very similar to like what the tag does down here. Where was that? Tag. Yeah, this is right here. Is comptime, and then for each field in the fields we basically just check if the builder get field value up is comptime, then if that's not comptime, then comptime is false. Perfect. And then in here, instead of this, we do builder.push. If is comptime, then a yogurt up comptime of a struct. of some fields. Yeah. Comptime fields will be this, and then for field in fields we do this, we do this, we do this. Builder get field dot value. Amazing. Okay. Okay, this doesn't work because getting a yogurt value to this map. Oh, right. We want to put something in here. We want to put field key into the field value, and then we have the content fields. Sure, the type is the same. Now type is this. Oh. That's what you get for just blindly copying stuff. Yeah. Okay. Hell yeah, for members, if the member of is comptime, you know, so just call this type. If member of is, well, that's first of all just is off used anywhere directly. Oh, down here. Compiler lookup. Sure. So that's an ID, I guess. This is only used there. Yeah, if better get off up is comptime, well, you know, we can basically do this. Comptime, first we assume that's true, and if one of the it's just this. That's it. So if yeah, then this is just a comptime thing. Just, I don't know, builder get, oh nice. If this is a comptime value, then we can just take value dot, it's a struct, yeah, so we can say value dot member name. Oh, hell yeah. Add type. Oh, yeah, this, we know this is a struct. Oh yeah, that's already a value. Yeah. Pretty cool, actually. I really like that. Okay. Yeah, the switch, we did that. Although, I should say, this down here, we can like remove this, basically. Oh, hang on. No, not really. Well, kind of. Yeah, if it's comptime known, then we have the value right here, we have the variant right here, we have the case body right here. That's the important part. Yeah, we don't need these. Nope. We can just say for id case body params do body dot push id, and same for the expressions. Yeah, we know that the parameters are all comptime. That's totally fine. Okay. Yeah, that's more like it. Beautiful. Like actually beautiful code. Okay, for calls we already like do that. We dig into the call and you know, yeah. Oh yeah. Yeah, here we kind of push two things, the call, because it can have side effects like panicking. And then the actual comptime value. Here just the call. Okay, I guess that's fine. Yeah. Then tag, yeah, has special comptime handling, and that's it. Okay, so I think everything should handle comptime now. Like everything should be as much comptime as possible on a like expression granularity or something. Yeah, so let's look at this. Oh yeah, here this is just enum apparently. Sure. What's going on here? So we call this with this type. We call this type info thing, sure. But then we just ignore that and create this comptime value instead, which tells us this is an enum of more with the name more at arguments of this type. And this is a list of int, yeah, a list of int types. And
the list of int and empty. This probably makes sense. What? Hang on. So this is the result of calling type info on the list of int is an enum. So far so good. An enum with one field of information. Information about what are the variants of this enum. Oh, yeah. It's specifically being called on an enum that can only be more, and int and empty. That does not seem right. No. So yeah, here we have this comptime more of one and empty, and then we call built-in type of more and one and empty. Yeah, of this type. Yeah, so then the result of that is just a comptime thing. And then we call foo with that more of int and empty. Oh yeah, that's what we do here. Okay, so this is correct after all. What we call type info. And this is a comptime value that we get back. Correct. Yes. But I think what's inside is not correct, because this is an enum with one payload that tells us what are the variants of this enum. And this is a list. It has more thing. It ends back here, and then it has an empty thing as the second thing. So there is only one item, like one variant in the enum. And that's not right. That is not right at all. Not right at all. Yeah. So this variant unit has the name more, sure, and it has arguments. Kind of like two arguments, I guess. More, and then it has arguments. That's this part right here. Yeah. And this is basically just int. Yeah, it has two arguments, int and empty. Also not correct. Not correct. No. This type info is not correct. But it's so short. Well, so we want to get info about an enum. That's great. And then we say, hey, give me information. Like this is a tag, correct? That's a type info, also nice. Tag enum, payload is this list.
yeah, so one payload, which is a list of these variants. I think yogurt value list just does not work correctly, because this happens like on two levels. You know, where you have the outer level of the names here, like the more and the empty variant is missing. Yeah, and then inside of that, for the arguments, it also only contains the int. I'm not sure. Yeah, I'm going to take a look at this. So we have items, which are yogurt values. Perfect. Yeah, should maybe. Yeah, this is yogurt. Typed. Oh yeah, here. Okay, it's not super long actually. Building comptime list of items. Please work. It does work. Nice. Building comptime list of items. Okay, so this really gives the wrong kind of data to the, yeah. So here, for example, we only have the more variant, and here we only have but wait, what we call foo. But then here we only like compiling type info of this other thing. Why though? Oh, because of the missing casting. I think it really is the casting. Yeah. Probably. Then again, at this point, compiling built-in type of this. Oh, this is already wrong, isn't it? Yeah, this is an enum with only one variant, more. Yeah, handle comptime casting. We really need to do that. So we can't just say this is the the claimed return type. No, the value also needs to be like receive the type. Compile cast fun body. Compile cast fun to unit of built-in. Okay, so I think I want to add something here. So here we have runtime casts. Here we have comptime casts. Comptime cast a value to a type. Returns a new value. Sure. Oh yeah. So what it does is it switches on the value. And of course there are things that we don't do. Like, oh yeah, the value time, of course. If it's an int, then we do there's not much we can do here. If it's a string, sure. Struct enum, int string struct. Oh yeah, it doesn't exist. Tag and type. Yeah, and only struct and tag are interesting. So, but before I do that, I should use that here. Comptime value dot comptime cast and return type. Yes. So if this is a comptime value, then we actually want to push a yogurt up dot comptime of that value comptime casted to the common type. Yeah, so we do this, and then we can just, yeah, let's factor something out. So we have something of a common type, and that something is this builder.push. Yeah. Look at how readable this becomes. What? Crazy. Honestly, this is crazy. Okay. Yeah. So we do a comptime cast in here. Nice. Yeah, of course we also, we need to cast these things. So if we have a struct, what we now want is a yogurt value kind dot struct of something of that type. Yeah. And this needs a map. That's what I thought. Yeah, the fields from string to yogurt value. And so for each field in the struct, we're actually going to put that into the fields map. Well, of course, now we comptime cast that to what type? Well, we know this type must be a struct type that we receive. So we can say plum type dot struct should extend the type one level. extend one level. Yep. This is a struct. We know that, so we can interrupt that, and then we can get the key from that. Oh, look at that. Nice. Field types. To try to create yogurt value kind.struct with nothing. With nothing. No. You can have the fields. That's fine. Okay. Yeah, same thing for the tag. Well, not same, but similar thing. Just take yogurt value kind.tag at the type. Yeah, and then there are the args, is what they're called. So we have archetypes of this thing. Yeah. Meh. Fine. Beautiful. Yeah, this is not a map. This is just a list. And then extend one level. Yeah, we know that's an enum type. And we also know the variant, which is, oh, I see. Tag.name, tag.variant, something like that. Tag.a, of course. Tag.a, and these are, this is like a list or a slice of types. Now we can zip that with the values. So values and the types, and those are from iterated over, and then we can take the, just push something. This is not a map, it's a list. Yeah, just take the values, so both dot a, comptime cast both dot b, like this, like this. Maybe not. Why? It's a tuple. Oh yeah, right. So we need a tuple of the tag symbol and this. Indeed. Indeed. Yeah, let's just try that. Okay, so we have some type comptime. Oh, this look. Does this? Is this different? I think it is actually. Yeah, I think in the previous version we didn't even have the recursive type. Can that be? Hang on, main. Yeah. Yeah, no, this was something weird. Yeah, it was just this. Oh, yeah, so although we call the list function, which, returns this upcasted list, we then call the type of function with the concrete value, that's correct, but not of the upcasted type, but of like the very specific value type that wasn't casted yet. Okay. So we have this. I'm kind of wondering. So we have enum foo. Yeah, this looks way better. So we have a comptime tag enum. Cool. With one payload. And this payload is a list. It contains this. So there's a variant named empty that contains no arguments. And there's a variant called more. And there are more variants. So one of them is this, and the other one is, that's it. So the second variant, more, it actually has a name more and has arguments. It has these arguments. Damn. So it has an int, and then it has another argument, so more, of a recursive type. Ooh. Not quite. Almost there. So the yogurt type info should extend the type when it traverses down into the individual fields. So if this is a struct, then the value type, yes, and this is not just for each field in the struct. Here we create a type just based on the field value. So iterate over the fields and do stuff with that. Same here, we iterate over the variants and do stuff with that. That's not good. We should instead have the type in here. That also must be a type. And let's extend that. Extend one level. Yeah, and here we switch on, oh yeah, as soon as we switch on the type, we basically need to extend it. That makes sense. That makes total sense. I love that. Okay, let's not do that. Let's keep that there. I'm sure. Crazy. Okay, so hopefully now it works. Hopefully. Okay, so we have a comptime value. Nice. Again with a list, an empty variant, and another variant. And this other variant, which is this, has the name more. And has these arguments. Oh, this looks good. So the first argument is int. And the second argument is this. Is more of that same list. Damn. That's crazy. That's crazy, honestly. What? Amazing. Okay, so okay, yeah. Let's let's actually like use this for something totally weird, but oh, amazing, honestly. Yeah, let's maybe do this. Let's say crazy. So prose description of something is I don't know, type info of type, yeah. You get information about the type. Oh, yeah. Let's turn this into like a German language. To Deutsch, which is basically to German and German is German. So this is Zahl. This is a string that Typ Struktur mit Feldern. Yeah, and here we want to concatenate. So it's the struct with fields. Let's concatenate these. Let's say, okay, I mean, for now, let's just print this, see if this works. Yeah, it says it's a struct. What? Okay, so let's, how can we like concat strings? I think there was like is there like a plus for ins and for strings? Okay, fantastic. Yeah, so let's call fields, which will be a list of field. Oh, this is so deranged. Honestly. Yeah, basically we switch on these fields. If it's empty, then there is nothing. And if there is more with a field and rest, then we actually print, we return field plus rest to Deutsch. Oh. Yeah, and let's just do this. Like the enum will work similarly, probably, but yeah. Struktur mit Feldern, and then the other part will be closing brace and like the fields to Deutsch. What? Yeah. Oh, hang on. No, because these are multi-line. They have to be like this. Let's use pipes here. I think that's clean. No. An error occurred, okay. Oh. Of course. field end. That is correct. There are 2 fields in there. Crazy. Yeah, field name, I guess. Yeah. And then basically, you know, if the rest is empty, like rest is empty. Ooh. Oh no. No, no, no. Or maybe this works. I'm not sure. I think this works. If the rest is empty, then just nothing. Okay, we take the field name, and then if the rest is empty, oh, I see. Yeah, let's do it like this. So we take the rest. Yeah, if it's empty, we just take the field name. If it's more of a B, I don't know, we take the field name plus rest to Deutsch. Yeah, name age, look at that. Oh yeah, we can also put an und in that, which is an and. So struct with fields, name and age. Okay. What? Yeah, also a single field makes sense to do that as well. Yeah, I think that's pretty easy. It's just the name. Then, oh, I guess, yeah, also the type of that. So the this and the field type converted to German, and that gets converted. Oh yeah, then like the type in parentheses, basically. Okay, and then oh yeah, this true. Yeah, okay, if the no fields is what it says. And because this will never be reached naturally, like, you know, if the rest is empty, then we only print the field name and we don't call ourselves recursively. So this empty is only reached if the initial list had no fields at all. Yeah, right, and here this returns a string. Okay, struct with fields. Yeah, I want to take the field and Germanize that. Same here. Oh, on type, that's not comptime. Hang on.
hang on. Oh, wait, so this should be a comptime value, right? Yeah, it should be. This should be a comptime value. I don't know how. Huh. Okay, let's see where things go wrong. So compiling stuff. Oh yeah, so concatenating non-comptime known string is already pretty bad in our case. Okay, so we have this. Perfect. I don't know what this exactly is, like. Weird. Seems like a list of these structs. Oh, yeah, list of the fields. That makes sense. Yeah. And they're comptime known, exactly. And there are a list of fields. Yeah, this is exactly what this is saying. Crazy. So the first thing we do is do that for the name, which is a field, correct. Yeah, we concatenate those strings at compile time. Then the second part. Oh yeah, compiling the... Oh yeah, that makes sense. So the first thing, the first field is a name of the type string. So after concatenating, like, hey, this is a name, opening parentheses, and now we want to type a stringified version of the type. So we're basically converting this string of type comptime known string of the type into German. We call type info on that. Beautiful. What we get back is this. What is going on here? So done compiling type info of string. What? And here we don't have comptime values anymore. This is only runtime known. And also like a runtime known field and so on, you know. I don't know why though. I have no idea why. Compiling type info. Yeah, let's maybe replace this for now with type, or like to do. Yeah. Okay, that works. But does it like... What was then the main function?
Okay, struct with fields of this. Okay, then we have a comptime string here. We call plus of this. Yeah, of this string and this string. Sure. Okay, yeah, so inside of the, I'm interested in this function. Name is age, type is int. Okay, so here we have a comptime age and opening parentheses, yeah, and stuff. Agent to do. I mean, the type is int, so that looks fine to me. Same here, except here the type is string. That's also like totally fine. But why if, yeah, I'm just gonna, because we don't optimize anything away, you know, we should see the type here. Oh, when we navigate into structs at compile time, I think we don't extend them. We don't extend the types. Can that be? So this is a comptime int. I know, no, extending is only relevant for recursive types anyway, so that's probably not it. Here we have a comptime string of the type. I just don't know how or why I don't get it. What exactly was the error here? Type info colon type, that's not comptime. Like, what? Type info of string. Yeah. And then we see, okay, field type is a type. Huh. Name and string. I guess. What? Why is this happening? You know? It doesn't make any sense to me. And I'll try to minimize that into something simpler. Maybe call this foo. Oops. So yeah, let's just say foo. Foo of a type is, I don't know, something simple. And this just does that. I don't know, something. Yeah, it just returns an int. This returns an int. And this returns an int. So we have a lot of the like string concatenation stuff and so removed here. And yeah, this actually makes no sense. Yeah, let's do something here. Does that still crash? Yes, it does. Okay, this is already, well, not super easy to read, but meh. I guess simpler, a bit less cluttered. Okay, so is it also if I only have the name? Yeah. What about if I have an int? Probably not. Well, like probably this has something to do with structs. Oh, really? What? Uh-huh. Then, like, does it really matter what we do in here? Oh, I see. Yeah, that makes sense. That makes sense. So here we basically want something else. Right here we want something that tells us, hey, this should only happen at compile time. This must happen at compile time. Please only evaluate the matching case. Yeah. Because this doesn't work for runtime values. Yeah, fine. Yeah, I see that this makes sense, you know. So I think maybe it makes sense to just have a different operator for, like, I don't know, some compile time switch. I don't know. We'll figure something out. But not today. Like, that's a bigger design issue rather than something you can easily fix. So yeah, here let's just say we're printing a field is just printing the name, but then we can also just do that directly, I guess. Sal, which means number. Indeed. Okay, I mean, this is pretty... So this now just says struct fields are and then the fields. Yeah, and let's maybe do something, write the code for enumeration as well. Cool. Yeah. Crazy. Oh no. Multiple functions match. This variant. Oh no. What's going on here? So this is of this type, which means that it is a list. Yeah, either empty or more, that's a list. Definition of a list. It's a list of these things, of things with a name, which is a string, and args, which is empty, which is a list of types. And maybe like variant and field are the same, but I think field should be, yeah, field is just a type, and variant has a list of types. So I actually think this is kind of weird. Or did we, like, no, well, I don't get it. Why is that happening? Oh, here are the two variants actually. Hang on, this is empty or more of string types. Yeah, that makes sense. But here is like type. Here is args. These are like completely different. Wait, what? Multiple functions match. That's crazy. Multiple functions match. Nope, they don't. So full matches, there are too many here. We don't filter them out well enough. What do we do here? We say for each of the name matches, we check that the arguments match, the count. Sure. We build constraints. Yeah. You know, if of all type parameters, we do things, and in particular we just do this. We have archetypes, which is a list of Plum types. And for each for each argument we... Okay, so we get the types of the arguments, I mean, sure. And then here we have the parameter types that the function expects, which we also push in here. And then the substitutions are basically these matched against these constraints. So argtypes matching argtypes against parent types. Let's just see what this prints. Matching this thing with args against this. What? No. No. Maybe also print looking for a function. Yeah. Just so we know where this starts. Also, I'm gonna take a quick break. All right. What's going on? Looking for a function, and then there are 3 possible matches. The first one hopefully doesn't match against this. And the second one is different. Yeah, this is like args, this is types. Completely different. And this one, yeah, it's this should match. I think like the second one probably also matches. We could test it, but I'm fairly certain. So what was matching something? What was it called? Matching. Matching this against that. What does it do? It just calls match against from this type thing. So match against. How does that work for struct types? We copied a bit of that, so I wouldn't be surprised if it doesn't work correctly here. So we have the concrete fields of the struct. Oh yeah, we have the generic struct type, which in this case would just be this. Yeah. And then we have the concrete fields somewhere. Okay, so this is one argument, which is either empty or more. Fine. And this is also an enum with either empty or more. I think for enums, we call match against, sure, but then what? Match against returns bool, and we ignore that. Yeah, that's not good. Let's just return false if that doesn't match. Yeah, nice. Yeah, let's maybe also do what? Yeah, let's try enums maybe, just for the fun of it. True. No. True or false. Built-in type of to Deutsch. Yeah, I guess. This should say true or false, something like that. Oh no. Try to handle that. What? Yeah, so things are not quite working all the time. Comptime stuff is weird. But it's pretty late. Like, it's exactly midnight. Yeah, so I'm not gonna... I'm fine with how it is for now, you know. So, yeah, let's just commit that. Yeah, I guess we'll start implementing type info, I guess, and push that. And now, yeah, I will like quickly review what we've done today, because it was like quite a lot. Oh yeah. So first we replaced our C backend with a custom backend, like a bytecode thing that then has a VM, which is like a small mini computer that understands some instructions, like please add 2 integers or something. And this is stack based and is way slower than the C implementation, but it's written in Martinez, so we can do more powerful things like compile things on the fly later on, not right now. And in general, we are more flexible with how what we want to do at runtime versus at compile time, because it's just all Martinez. We don't have this completely separate step of now we are in a compiled language, completely different environment, and so on. Yeah. Then we implemented, overloading based on not just the types of arguments, but also the concrete values. So you could have something like a:type as a type parameter, and then use that same a as the type of a different parameter, and those two need to match. So if the first a is a compile time known type, then that needs to match that other one as well. Oh, we create structs through the entire compilation pipeline. Yeah, and we in general implement a lot of stuff at compile time now. Like a lot of stuff. Basically all of the operations that we emit. Before we do that, we check, hey, are the the things that they depend on, are they compile time known? If so, then we don't actually push these new operations, but instead we just push compile time values. So basically, it's called constant folding in many languages. Yeah, we do that now automatically. And finally, we also at least started to implement the type info function and support for that. Yeah, and it kind of works, but kind of doesn't. So parts of it work and others don't. But I guess that's fine. Okay, yeah, and I guess with that I will see you next time. Bye.